later ook dus.
Ja, meneer Baltus? Peter? Mag ik je beter noemen trouwens? Mag je beter? Ja. Ja. Moet je deze ja. Mag je het wel even beter? Ja, natuurlijk. Ja, nee, heel graag. Ik luister naar van alles, maar beter was. Ja.
Hallo. Ladies and gentlemen, welcome. My name is Peter Baltus, and today I'm your host for this workshop. It's a special workshop at the end of the Phoenix project, and I'm very glad that so many of you came here to this place to listen to everything that we've done and to see what the results of all that work has been. So to give you a little bit of background, the Phoenix project started 4 years ago in 2015, and the goal of the project was, in general, like for any future emerging technology program, to investigate, to create and to test really advanced science fiction-like technologies. And the goal we set ourselves was we want to explore environments that we don't know and that we can't get into. And you would be surprised once you start thinking about it how many of such environments exist and how difficult it is to get information from them. Basically because to get good information you need good sensors, and to make good sensors you need to know what they need to measure, and if you can't see what's going on in there and you don't know what it looks like, making a good sensor is fundamentally difficult. So we set out to find a way to solve this chicken and egg problem, that we needed to make a sensor that's optimized for an environment that we don't know, so that we can get to know the environment. And we wanted to do that with real-life applications, because many of us come from industry and we still enjoy developing research results that can be used in real life and not just for publications in journals. We were very lucky and we very much appreciate that we received funding from the European Union for running this project. We received 3.6 million euros, and we're very grateful that the European Union funded this project and has supported us throughout the project so well in many different ways. That's also one of the reasons that you see all these cameras standing here. We are live streaming this workshop, and part of the reason is that the reviewers of this project are also now having the possibility to see this workshop without having to travel to Eindhoven, of all places. What I'm going to show today is essentially the largest part the results of the Phoenix project. But there's also some results from other projects that you will see today that are logically related to Phoenix, but are not formally part of the project. For you that doesn't matter, but it's important for the reviewers, because on Monday, when we have the formal review of this project, we will leave these things out. The research, all this money, was carried out, and the money was spent by a team of 7 organizations: University of Leuven, University of Aachen, Eindhoven University, the Antea Group, University of Groningen, the University of Amsterdam, and the University of Trento, and for the first part also by a research institute called Incastri. Unfortunately, that institute stopped to exist halfway through the project, but their results are still taken into account, and they're still being credited, of course, for their contribution. So what are we going to show you today? Well, this is the program. Let me help you a little bit, seeing through the details. So these are the important things, right? The coffee at the beginning you already enjoyed, I hope, and the sandwiches. We have a break with demo and posters halfway through. Then we will go to a different building, matrix building, where we have a demo setup that you can go and see how things work in reality, and that we are not just making PowerPoint. But since we are such a large group, we will split in 2 subgroups, and I propose to do that left half, right half, so that we don't crowd the setup too much, and we'll help you with splitting up and going to that place during the break. And then at the end, we have drinks again, and at the back there are posters giving you more details of things that we have done that we couldn't fit into the presentations. So what are we going to see in presentations? Well, after this introduction, you're going to get a keynote by Kai Buist, and he's going to tell you one of the applications that can benefit from this technology, so that you have some idea why we're doing this. Then Marianne Verhelst from Leuven University will give an overview of the technology that we address. So what are we doing? How are we approaching this impossible chicken and egg problem of optimizing sensors for an environment that we don't know? And then just before the break, I will give you at least a very quick overview of the results that we achieved. And after that, I promise you, you really will need a break. So then we go to the demo. After the break, we will come back here. We will have presentations about the sensory nodes, about the circuits and transducers for the sensing, and finally a presentation about how you can use this in the future in industry. Then at the end, we will have some discussion, and then finally the drinks and the posters. So for now, I would like to stop talking and invite you to sit back, to enjoy the program. And I want to invite our first keynote speaker, Kai Buist, because he's going to explain to us how you can measure by floating. And that sounds like a really nice job description. Maakt het heel goed?
Okay, thank you for this kind introduction and the invitation to come and talk here about measuring by floating. And unfortunately, the subtitle was missing from the program, but it's actually about mote interactions in multi-phase flow. You can see a short example of what that actually means. We have the mote here, and the multi-phase aspect is actually, in this particular case, mostly focused on bubble column reactors. But since you are not all familiar probably with multi-phase flow or with bubble columns in particular, I will give a short overview of what that means and what are the main parameters that are important in such reactors. I'll tell you a bit about the currently available experimental techniques to measure those parameters, and finally also show you what the motes can do in these environments. So, multi-phase flows are key flows in the chemical industry and in processing industry. And often what is needed is that you have these multiple phases that you have to get in contact to, which can be, for instance, gases which have to come into contact with a catalyst in order to transform those gases into valuable products, or for instance, a particular gas stream which has to be stripped certain component, which is often done in absorber bubble columns. Or finally, in spray drying, for instance, which is a key Dutch technology to dry milk products into milk powders. And all of these flows are what we term in our research group dispersed multiphase flows. And what does that mean? Is that it has a main flow of a fluid, either a gas or a liquid, and dispersed elements, which can be bubbles or particles or droplets. In this particular project, we're interested in bubble columns. So bubble columns are a type of reactor which is often used in, for instance, aeration processes, which can be fermentation to make certain proteins or other products, in wastewater treatment, in absorption processes, or in the petrochemical industry, for instance, in wet oxidation reactions. There are some applications also in metallurgy, which is mostly, for instance, desulfurization. And actually all of them have a few things in common. We just have a liquid, and we bring in a gas through a starter system, which has one main purpose, which is to break up that gas into separate bubbles. And you want these bubbles to be relatively more or less as small as possible, because that means that you have relatively the most surface area for mass transfer. Now, typically such a bubble column reactor can be quite large, on the order of 100 cubic meters, and can have gas holdups of 25 to 50%, depending on the application, with bubble size distributions ranging from a couple of millimeters up to a couple of centimeters. And a lot of these parameters are key in how well this process is performing. And all of these parameters are often interdependent also. So if it's a chemical reactor, of course you're interested in the chemical reaction rate, or the mass transfer rate. But these two parameters often depend largely on the gas holdup, the bubble size distribution and or shape, and also the relative velocity of the liquids and the bubbles relative to each other. So it's these kind of parameters that you want to control, possibly, but in an industrial environment also want to be able to measure, which is not that trivial. So one of the options is, of course, to use a camera, but in industry this is not possible because you usually don't have optical accesses. There's a number of different techniques that can be used. For instance, tomographic techniques. In this particular case, it's ultrasound imaging, but you can also think of X-ray tomography, which in essence just sends a signal through your sample, which can be picked up by a number of sensors, and then from that you can do a tomographic reconstruction of the interior of such a flow. Usually this is just one particular plane in your system, and because this signal is decaying over the distance, typically the size of such a system is restricted to 10 to 30 centimeters in diameter. So it's not nearly as big as you want it to be. But for academic purposes, this is perfect to validate computational models, for instance, which is often what we are interested in research. Alternatively, you can use a number of probes, which you can then put inside your reactor. But of course, they are intrusive, and you can only measure at one particular location inside the reactor. And such probes can be these dual tip conductivity probes, which can actually make a distinction between whether or not between these two tips there's a gas or a liquid, depending on how conductive they are. And that way you can make a distinction between the phases locally. There are some alternative probes as well, which can be either piezo or pressure sensors. Optical fibers are also often used to make similar estimates. There's a number of optical techniques that we can use. For instance, high-speed imaging, but also laser-induced fluorescence, which is actually capable of determining the mass transfer rate. So with laser-induced fluorescence, you can, in this particular case, look at the CO2 absorption from this gas bubble into the liquid, particularly in the wake of this bubble. Now, of course, we need optical access, but also these systems are restricted to very low gas holdups, because the more gas there is, the more view is obstructed. Now, a first step to what we actually would like to have is a tracer. And a tracer is actually just a single particle which emits a signal which can be measured from the outside. Now the nice thing about such a tracer is that it can freely traverse through the entire system, and it can give you information on its location, for instance, which is often done by radioactive decay, for instance in radioactive particle tracking, or we term positron emission particle tracking, which is more or less a derivative of the PET scanner, which you know from medical imaging. But it can also be a magnet, which has a magnetic field, which can again be measured by a set of sensors. And from that you can do a reconstruction of the position of that tracer into the system. So you know something about the local flow rates in such a fluid. And that's where these motes actually come in. These motes are freely floating sensors, which can then give you some information of what's happening inside. And from previous projects, which I have seen from for instance, we've seen that it can be used in single-phase media, and it can tell you something about interactions with solid surfaces, be it an impeller inside a mixer, or flanges in a pipe system. But we said, okay, if we can measure these hard interactions of a mote, then possibly we can also measure what we term softer interactions, in particular with a bubble. And if that's the case, then the mote should be able to tell us something about the local gas flow rate or gas holder. Maybe the bubble size distribution, and maybe also these individual interactions of a bubble with the mote are visible. And if so, that can tell us a lot about the performance of the bubble column reactor. Now that of course means that the mote must still be able to freely move inside the reactor and not get stuck in recirculation zones or in so-called dead zones of the reactor. Now, this is one of the motes that we've used. I think this is an older model. But the nice thing is that we can density match this particular mote just by adding weights. So what we did is we density matched it to water. And the funny thing is that because the weight of the mote is off-center, it has a preferred orientation. And this preferred orientation is actually key in being able to determine these interactions. So one of the first things what one of my bachelor students did is try to measure impacts of different surfaces, just to see if indeed we can make a distinction between these different surfaces. And actually I think he dropped it from quite a height, which more or less scared Heinrich. In essence, we were able to see that there's differences between the impacts of different surfaces, especially in their impact times. And that gave us enough confidence to proceed. So we took one of our old setups, which is actually capable of capturing air inside a cup, and then by switching the cup, we could release the bubble of different volumes. So we strung the mote from a fishing wire, so that it's positioned nicely above the cup, and then we look at, for instance, the accelerometer and the data from the gyroscope, which is a rotation. And this is what we see. So on the right we have a video, maybe I can play it again. No, it doesn't want to. Go back first. No, sorry. In that sense, what you see happening is that you get an initial bump in the rotation, which is actually the fluid which is being displaced by the bubble just in front of this bubble. Then we see an initial very sharp peak, which is this bubble impacting, and then we see this nice slowly decaying harmonic oscillator, which is actually the mote slowly dampening its motion through the viscous fluid. So indeed we can distinguish the interaction of a bubble with the mote. Now we thought, okay, maybe this initial peak, the strength of this peak, relates to its bubble size. So we added different bubbles to the system and looked at the initial data. And indeed, from both the gyroscope and the accelerometer, we were able to distinguish what the size of the bubble was, the single bubble impacting on the mote. Now, you might notice that indeed there is a correlation, but also that the bubble radius is quite restricted. So we initially said the bubble size distribution in a bubble column reactor is of the order of a few millimeters up to a few centimeters, but we're at the moment not able to look at these smallest bubble sizes, which means that the mode is probably a bit too heavy. Okay, so next thing is to look at an actual bubble column to see if we can correlate to the flow rate of such a system. So my student dropped the mode in an actual bubble column, which is more or less 17 centimeters in diameter and just a meter tall, and just played around with the gas flow rate, just to see what's happening. And there's a few things that are quite striking. First, of course, this mode is capable of traversing throughout the entire reactor. And second, you can clearly see the preferred orientation with the vertical axis of the mode, of the two halves being in vertical plane also. And that indeed, the rotation of this mode scales clearly with the flow rate of the gas. The same in principle also for the accelerometer, but it's maybe less clear. So we also did it in the old setup, and by looking at the superficial gas velocity, we could again correlate the absolute of the amplitude of the gyroscope and of the accelerometer to the local flow rate. Now the last thing is also that we of course want to be able to tell something about the individual impacts in such a system. And this is of course much more difficult. So where we see an initial very sharp peak for single impact of a bubble with such a mode, now we see, due to this continuous striking of the mode, that there is less distinction between what is actually an impact and what is the damping of the mode itself. Okay. But it is possible, hopefully. So the first thing that my student tried at least is to try and match from these videos if there's a particular event and if we can see some form of a reaction on either the accelerometer or on the gyroscope. And for some of the instances it was quite clear. You can see very clear peaks in the data, especially for the gyroscope, but less so for the accelerometer. But in principle all of the information is still there, but with a lot more analysis is needed. So to just shortly conclude, these modes are capable of moving freely in a multiphase medium. And the data from the gyroscope and the accelerometer clearly correlate to bubble impacts of a single bubble in a quiescent fluid. They do correlate also to the local gas flow rate, and they could possibly correlate to individual impact frequencies. But determining the bubble size in an actual bubble column would probably be much more difficult, which is due to the fact that you have constant impacting and damping of this mode, and possibly due to the relative velocity of the bubbles with the fluid and with the mode itself, which complicates the matter. So from these single bubbles, of course, the fluid and the mode are initially at rest, but when it's moving through the entire system, the relative velocity of this bubble with the mode will give a very different signal. Of course, much more analysis is needed and possible. And last but not least, the mode is possibly slightly too heavy for actually to be able to be used in industrial flows. I also have to acknowledge a few people. This is, of course, the Professor Heinrich Werther, we've had a very interesting collaboration with. My PhD student Satish Kamat, which I threw headfirst into this problem, because his project's actually on slightly different applications. And the two students, Arne Valk and Dylan Lanton, who were brave enough to take up this challenge. And last but not least, Dr. Engineer Dekan Krijgers for his help in understanding the modes itself. Thank you for your attention.
Thank you very much. Ladies and gentlemen, are there any questions? Yes, please.
And many graphs I saw error bars that were as large as the range of the graph.
Yes.
So is it really useful in practice and in such a manner?
Well, mostly what we're interested in such flows is to be able to determine locally what the flow rate is. There the error margins were quite small. And to be able to distinguish what the bubble size distribution is. So possibly the individual impacts are not as important as long as we know the distribution itself. Now, why these error margins are so large is because and I've not discussed it very clearly, is that the impact of such a bubble with a mote depends heavily also on where it impacts. So if it's head on or just on the side or slightly far off from the mote.
Further questions? Yes, Martin.
I was just wondering about the results. Did you try to analyze it more in detail? Let's say, for example, apply some like filtering on the because you said you couldn't really see the impact of the bubbles, but did you try some processing signals?
Yes, we did. So indeed, especially for the accelerometer, we needed quite a lot of filtering to be able to distinguish some of the behavior. So we did apply some filtering there, and what I of course showed now was just the magnitude of these components, and we have not looked at the angular components just yet.
Further questions? Yes, please.
How did you get the data out?
How did you get the data out? How do you mean?
Yeah, well, my assumption is that you have a memory card inside where
Yes.
you record all the data.
Yeah, so all the data is stored on site on the mote itself, and then you can read it out via a mini USB, I think.
And that's also the size limitation, or is the accelerometer the size limitation?
I'm not exactly sure what the limitation of the size is.
But that is something that will come back in the next presentations. So that question will be answered by Marianne.
Okay, yeah.
So we took just one of the older modes off the shelf and used it.
Because you said you wanted to have them smaller for better accuracy of smaller bubbles.
Yeah.
What's inside can determine the total size as well.
Yes, please.
If you have videos of the same events available, then I would assume that you do something like machine learning to extract the real events. Is that something you try?
Well, you have to imagine that this is very preliminary results. We only had 2 students to be able to study this, and a PhD student who is doing this on the side. So we don't have the time yet. But for machine learning, you need a lot of data. And at the moment, the amount of data is, I guess, too small to do machine learning.
Again, this is something we will come back to, but it's a very good point.
Yes.
I think Arthur.
You do these experiments to characterize the multi-phase flow.
Yes.
But you have sensors in it which surely will influence the situation. So how sure are you that you measure something which is characteristic for a flow without sensors?
That's a good question. And it's actually somewhat similar to what you'd have with inserting a probe. Yeah, there you have the same problem, and what you see is that typically this probe will tend to underestimate a bit what's going on actually inside. The thing is with these modes is that they are more or less moving with the medium itself, which makes them less invasive than these probes because they are static, but still more invasive than if there would be no mode at all. I agree.
Further questions? Yes, please.
Yeah, I'm not familiar with the research, but I think that I understood that you measure the rotation.
Mm-hmm.
Is that correct?
Yes.
Did you somehow optimize your mode for rotation?
No, we didn't. So the mode naturally already has a mass distribution, and by adding the weights, this is somewhat amplified. But we did not optimize it. So you can indeed imagine that by placing the added mass a bit further away or a bit closer to the mode, you can more or less try to optimize the system a bit.
Yeah, the shape now is a ball, a sphere.
Yes, true, yes.
So I could imagine that you make it a little bit different to be more sensitive to rotation.
That's one possibility, but because the mass distribution inside the mode is already off-center, you already have this tendency to realign. But there's a balance a bit between it being too heavy and not showing any data, and it being not heavy enough and just start to rotate all over the place. So if that would happen, then we would not see any data anymore.
Further questions? Yes, please.
Yeah. Did you consider other sensors except for the motion sensor?
Well, there is magnometer, I think, in there, so it can measure magnetic field, but inside the chemical reactor I'm not sure how sensible that will be. Of course, the ultrasound transducers, which are part of another project, I think, could give you some indication, possibly, of the local distribution of the gas as well. But you can imagine having temperature or pressure sensors, for instance. Yeah.
Any last questions that you really need to ask, because otherwise you can't sleep tonight? If not, then let's thank Kai once more. Heel erg bedankt. Bedankt. And then, ladies and gentlemen, we go to the next presentation where many of the questions will be answered. A few things that I might want to remember from this presentation is that it would be nice to have smaller sensors. And at the same time, it's difficult to find out how to interpret data from that sensor to get the answers that you want, and how to modify the sensors to get the data that you're looking for. Now, this is a very fundamental question that comes back in many applications that we are targeting, and that's also the reason that we worked on the technology that Marjan is now going to explain. So Marjan, can I give the microphone to you?
Yeah. All this long hair. Okay, like this?
Yes.
Okay. So indeed, I think our previous talk was the perfect introduction to what I want to show you. So you have seen just an application where you want to sense things with as minimal disturbance and effort and manpower as possible. And it makes us dream, because this was one application. But what if we could enable this for so many more cases? What if we could really explore many things from the inside without having to be too intrusive? Think about very long pipelines where now people have to manually go by or send drones over the thing to inspect whether there is a leak or there is a corrosion problem happening, or maybe people are tapping off something from the pipeline. What if we just could send sensors through and sense what's going on there? It would require a couple of things. We would have to be able to sense many things. I'm not just happy with an accelerometer anymore. Maybe I want to sense pressure and temperature, and maybe do some ultrasound measurements to sense corrosion, or a biochemical or a chemical measurement, many parameters. The modes have to be super small, because indeed they have to not influence too much what's already going on there. Maybe they have to go through small pipes from time to time. And I want them to have a pretty long lifetime. I cannot drop them there and then 50 minutes later go get them back. No, maybe they're traveling for hours and hours before I get them back. So their battery life has to be very long. What if? What if we could do even more than that? What if I could deploy such a thing on massive scale across wide spaces to not just sense one pipe somewhere, but sense larger areas where there is fluids or gases and so on, to maybe even not just sense what's going on there, but have so many modes that can go around everywhere that I can even make automated maps of these kind of environments. Maps of sewing systems, air venting systems, and so on. It would require more than just sensing. I have to do localization and so on, and this at a wide scale. Many needs. What if? What if I could not only do this at places where I can still get near the pipe, but even at places that are far away, ducked under some soil or very deep in the ground, where now I have to basically remove the ground and make holes, lots of effort? What if that was not needed? If I could really measure at a place where a human system cannot get, where I cannot even communicate to anymore. I don't have to have access to my mote or be near my mote. It just manages by itself. Here I could still open up the ground, but in many cases I cannot. This is an underground oil well, where You pump in CO2, the oil comes out. What if I could send my sensors in? They can figure out what's going on down here. When they would come back out, they can tell me. But I cannot communicate to them when they're here. This is many, many, many meters, kilometer, whatever, of soil. There is no way that something here can talk to something there. So these sensors don't only need this. They also have to be able to have enough intelligence to operate autonomously for quite some time. Pretty challenging, but what if we could do all of that? Then we can really explore unknown spaces. You can send your sensors out to a place you don't know, it comes back, and you gather more knowledge about this environment. And there's many, many applications that we saw that would become possible. So that's exactly what the Phoenix project was after. How are we approaching that? What I want to show you is the concepts behind our ideas, and then Peter will go deeper into the practical implementation, where you get more and more details throughout the rest of the afternoon from individual researchers. So, many of us here are engineers, so how do you approach such a problem? These are my needs, these are the things from the bottom here. My requirements, this is what I want. And I'm an engineer, I have to build something that can sense and so on and so on. So I want to take a robot. And I need a robot and I need many sensors. So I take many sensors, I put them in my robot, and I'm happy I have many parameters. Of course, I also want a long lifetime. So I give my robot a big battery. And now it can sense for many days. But of course, it's no longer small. I cannot really buy thousands of them because they're extremely expensive. I'm a bit stuck between being small and live for a long time and buying many of them for low cost. Doesn't seem to be the perfect solution after all. So what else can I do? Well, I'm an engineer, I can make something cheap. So I just take a very small system like a ball that we saw, and I give it some memory and a processor die, and I put many sensors on top. Or maybe not many sensors, it's too expensive. No, just a few sensors, only the ones I need. An accelerometer, a pressure sensor, for example. So now it's small, it's just what I need. Probably doesn't consume too much battery and can have a long lifetime, and it's cheap to make many of them. But I can only sense one thing or a couple things. Maybe only pressure and accelerometer. But depending on the environment I'm in, I might be interested in different things. In my oil well, I also need to know the pressure, but in my chemical system, I want to know temperature, and somewhere else I want something else. Okay, what you could of course do is make different versions of this platform. One that goes into water pipes, and one that goes into my oil well, and another one for my bubbling pipes, because you can have a very nice shape that aligns with the bubbles. So you can change the shape and the content of each platform depending on your need. And now it is small and cheap, and still I can adapt to the different cases that I want to support. So if I compare these to my robots, seems an interesting solution, because now I have something that at least I cannot sense everything, but I can sense what I might need for a specific environment. But there is a but. How do I know what environment to optimize for? Because I want to explore a place I don't know. I want to send a mote down a very deep trench into the earth, for example, and it will come back 2 days later, but I do not know what it's going to encounter there. So it's an unknown area. What parameters should I best sense? Do I have to only sense with my gyroscope or also with my accelerometer? And how often should they sense? 1 kilohertz sampling rate, 100 hertz or 15 kilohertz? I don't know. How accurate should they sense? I don't have a clue. How long will they be in there? It's a new environment. Do they need a battery life for 1 day or for 10 days or 1 hour? No clue. Should they be big or small? Is it a small pipe they'll have to go through? Or a big area they're going to explore? What shape will they optimally need to align to whatever fluid and density they encounter down there? How many of them do I need, and so on. I'm optimizing a problem for which I do not know the constraints. That is very hard. You cannot really design a system and optimize it for something you do not know. So that was the problem we were facing within Phoenix. And that's exactly what Phoenix tries to tackle with a concept that we denote as intelligent versatile sensory swarms. What does this mean? And I'm going to take a sip. Well, let's start from the basics. We are working with a swarm. A swarm basically meaning that we make many, many simple sensory agents. Like the balls that you saw, some of them targeting smaller sizes. We make many of them and they're going to collaborate. So they're a swarm that can collect information everywhere. They are versatile, which means they can change. So they don't have to be all the same. The first way in which they can change is they can change at fabrication time. So I can decide to make a mote with a different shape, with different types of sensors, with different sampling speeds or sampling accuracy for every sensor, with different processing power. I can add a big battery in one or a small battery for small size in another one, and a big memory card or a small memory card depending on the size, and so on and so on. At this moment, I do not know what to optimize for, and I'll just have to make a guess. I'll make a pick, and I'll make a combination of this in my motes, and I do not even have to only make one combination of them. I can make a few types of motes. And in Phoenix, we call this casts. Like the caste system, there is different groups of modes that have different characteristics, different behaviors. Maybe one type of mode are pure sensory modes. I equip them with a nice sensor board where they can measure pressure, accelerometry, and so on, and they just start to sample what they see in the environment. Other modes are not spending all their power on constantly sensing data. Instead, they will search or serve as communication hub. They collect information from some of these guys and share it such that if a few modes get stuck, their information is still retrieved and taken to the outside world. So they share, they're like information mules that gather information from others. And others could maybe be modes that are made such that they sink to the bottom after some time and they stay there and they serve as beacons for others so that others know, oh, now I passed mode 67, so my measurement at this point can be correlated to a measurement of someone else and so on. So again, at this moment, we don't really know what mode would be the optimal one, but you see, based on the parameters we can change at fabrication times, we can make different groups of modes, each with different characteristics when they're made, and they will fulfill some roles in the environment. But how do we know what roles they should fulfill, or what the best sampling rate for this guy is, or when they should communicate, and so on? Well, let's see. At the beginning, we don't know, so we just generate some groups of modes, and we send them into our environment. They're just launched down there. They go down, and they start to do what they're programmed for. The purple ones start to sense, take maybe some coarse measurements from time to time. These ones start to collect information from others. The red ones maybe sink down, and they're beacons for other modes that pass by, and so on. And after some time, turns out they did some tests with actual oil well companies, and it takes like 9 hours or something, I think. The modes come back out, and you read out what they observed. You will get knowledge about this space. You will not know everything about the space. These modes were not optimally conditioned to sense what's down there. Maybe the accelerometer sampled too slow, and the communication wasn't good enough, or the battery of these guys died too soon, and so on. But you'll get some knowledge. You know already a bit more about the space than you knew before you send in these guys. This bit of knowledge you get, you can use to make a first model of the thing you're exploring. A first crude model that doesn't solve all your problems yet, but brings you a step further. Because with this model, I can now start to learn what modes would have been better modes for these environments. I can start to learn the better characteristics of the mode. Does my sampling rate of the sensor has to go up? Does my communication has to happen more frequently? Do I need more beacon modes but less communication modes? So you can start to learn what the optimal population of your system of sensors is, of your swarm is. The optimal groups of populations you want to have and what every group has in terms of characteristics. We don't just basically do one simulation and then send new modes back in. No, here we do with machine learning. You will see that. We do several iterations of new generations of modes that are created with some evolutionary algorithms. They're tried out on the virtual model of the environment to see whether they indeed are better explorers. And this can iterate several times until we think, yes, this new swarm is a better swarm to go down there, much better than what we had before. That new swarm, which is still virtual at this point, can then physically be created. So we make new modes or update the settings of the modes. Maybe these ones will now sense a bit more often. And these ones are maybe now joined beacon and communication modes for some reason. So you learn better groups of casts and characteristic of every cast. We physically create them, and this improved set of sensors goes back down there. And they're better fitted now for the environment. And there's kind of a rebirth of our modes. The modes we had, they die, and they reborn or get reborn with better characteristics. With survival of the fittest, or we denoted the project Phoenix, because from the ashes of these modes, new modes get born like a phoenix that rises out of the ashes. So this is the first important concept of phoenix. You have generations and generations, because this iteration can take place many times. You have generations after generations of sensory agents, where every agent is better and better adapted to the initially unknown environment of the place where I cannot get to. And you really get a kind of ancestry tree of sensory modes that for every environment, a different mode will eventually come out. But we're not there yet still. Because this concept works nicely if the environment you're trying to analyze is a very homogeneous environment. If anywhere the mode goes, you want it to have the same behavior. But that's in reality not the case. Because many environments, think about our oil well. Well, if it goes down to the oil well, if it goes down into the oil well, maybe in the beginning there is not much oil and the pressure is low, but a bit further the pressure builds up and the temperature goes up, and then somewhere else it is a larger space. Very often, if the sensor has to behave optimally, it will not everywhere in the environment behave in the same way. Another example is a sewer system, that if the sewer just goes straight, you sample slowly, but if there's lots of turns and bends, you might want to sample at a much faster rate, because there is more information to capture there. So we want our sensors to not only be customized into fixed set of parameters at fabrication time. No, we also want them to be smart enough that at runtime they can change their own behavior depending on what's happening. So we would not only customize, for example, the sampling speed in a static way. You accelerometer, you sample at 1 hertz or at 1 kilohertz. No, you want to say, accelerometer, in this situation you have to sample that fast, but in that situation you sample that fast. The system has to become self-adaptive. How it becomes self-adaptive, we can again learn. Do you want the system to know itself how to react in which environment, in which circumstances, basically? So, what does this mean in practice? Well, a cast that we defined before like my sensor cast, it will no longer be statically defined. It will be a dynamic system that you define, where you say, this cast senses, for example, speed at this sampling rate and pressure at that sampling rate. But if there is many nodes nearby, he stops sampling because others are measuring already. So you kind of make conditions or scenarios in which the behavior of a certain cast changes. Another example, the beacon node will become a beacon node, but there is a random amount of time before they wait until they sink down and become a beacon. Or a communication hub will change its communication behavior depending on how rapidly the node is moving. And so on and so on. So you see that you want adaptive behavior from these modes. Now the big challenge that we had in Phoenix to realize that is that we want an adaptive system, a self-adaptive, so it's self-controlling, it's intelligent behavior, but our modes don't have any resources. They have hardly any memory left because we want to store the data there. They have hardly any compute power because they have to run on a super low power 1 microwatt whatever battery. So how can you generate such intelligent behavior of online adaptivity without almost any compute power? Well, the concept we implement for that is something we call an instinct. An instinct, also for us humans or animals, is something you do, a reaction to a sensory stimulus you do without even thinking much about it. I think of a baby that doesn't really use lots of brain power to know if you put a finger in their hand, they're clamping their hand around your finger. They don't think about it. It's instinctive behavior. Or if you would try to hit me, I will close my eyes. I'm not really reflecting much about closing my eyes. It's an instinct that's built into me. So an instinct is really changing behavior. As a result of a sensory input, do something. So, for example, if a certain sensor value is larger than a number, then stop sensing. Or if I'm at this location, then start to communicate more. There are kind of rules that we let our casts, our sensor nodes, know. Of course, this is very simple rules. In reality, in our project, we work with much more complex rules that we implement through something called a behavioral tree. And such a behavioral tree captures the adaptive behavior of the mode in a very compact and efficient way. And again, how does this fit into the big system that I showed you before? Well, we again will have casts that go through the system. They come out. Based on this knowledge, we build a model of the environment. But what changes now is that in the evolutionary algorithm, using this model to find the next group of casts, we are not only changing static parameters like shape or amount of memory and battery size and so on. Now we also here evolutionary evolve the instinct, the behavior of the system when it's down there. We learn in an evolutionary way the best instinct of a certain mode so that it will optimally behave or have an optimal adaptive behavior when it's down there. Voilà. So that's kind of the central concepts of the Phoenix project. So where we are really striving for intelligent behavior of autonomous swarms, of very small modes with almost no resources or power consumption, and doing that through very flexible, versatile sensors, but that are evolved over generations of different sensors, where we evolve both their static parameters as well as their behavior or adaptive behavior through something we call the instinct principle. Voilà, this is the concept. And then later, of course, you want to see, okay, how you do that. The rest of the afternoon will deal with many of these aspects. Thank you.
Thank you very much, Marjan. Are there any questions for this piece?
You propose an evolutionary algorithm to update the nature of the modes. How fast does that converge towards the modes that you want?
Yeah, so the compute time of the evolutionary algorithm is a bottleneck. And we even see that in our simulation. You will see a demo today. You'll see that it takes time. Now, the idea there is that let's take our example of the oil well. You're sending something down here that will take a day or something before it comes back up. Thousands of nodes might go in there. You really are okay to spend a day computing what the next generation of your modes would be to go down, because it's a big investment of a whole exploration.
I was mainly thinking about the cycle time.
Every time, yeah, you have to go through maybe a couple, 50 times or something, and it all depends on how efficiently you can model this environment. And I'm not the expert here, but there's people in the room and a talk later, so yeah, you better ask them these questions. But yes, it's in the critical loop. But because this is quite a big investment in your measurement campaign, it is okay to really spend a GPU server and so on this side, basically. And maybe also important to notice is that the first time I go into an oil well, I have to learn from scratch, and I won't know anything yet. If I go to a different oil well, there might be a different environment, but many of the information I already had can also be reused. So new environments become easier if you have seen a similar environment in the past. Yeah.
Maybe good to emphasize also that we have the experiments that loop to improve, but for every single experiment, we run many simulated experiments. It can be hundreds of thousands. Before that, we do a real-life experiment again. So most of the evolution actually happens in virtual life, and that helps to speed up the whole process. If we had to do every iteration through the oil well, I probably would have seen an environment before that we
Yes.
Do the modes react on each other with their sensory? Because then you could get a kind of oscillation that they keep reacting on each other.
So the modes we are developing, ideally, because it's not everything is fully set up yet, but they have ultrasound communication capabilities. So they can give information to each other. Now, at the moment, we're only envisioning this, that they can figure out who else is nearby, and not yet that they're exchanging information, like I'm now sampling that fast. But if you make them more intelligent, you could even build that in. It's a kind of other rule. If I see someone else share this information, and if someone shares this thing with me, then do that. These are all kind of behaviors you could configure, but we haven't exploited that fact.
Yeah, because you could get, if they interact strongly, then you can get, okay, oh, there are all the nodes nearby, then I can switch off, and the other think, oh, he switches off.
Yeah, but if that kind of behavior would be a problem, our virtual simulation would capture it, because it simulates the modes with their instincts, and it would see, with this instinct, I don't get anything anymore. Right? So then the virtual loop would say bad ID, and they would try something else, and until you really find an instinct that gives a very good information capture, and only that one is sent down there. Yes. Yeah.
Further questions?
Yeah.
So how, quite practical question, you don't know the environment that you will explore. How do you choose the container where it's made of?
So I say we want to explore completely unexplorable or unknown environment, but of course you always have some expert knowledge. So in our group we also have people, ontology people and expert knowledge capturing people that basically try to capture what you know of an environment and inject that into a first generation optimizer. For example, if I go in a sewing system, I know there is some water and I know what contaminants are typically going to be there. I might not know the exact shapes and the sizes of all the tubes, but maybe I know the minimum size tube that's used in here is typically this. So there's always some expert knowledge that is around. We'll capture that, and based on this expert knowledge, we just do the best we can. And if you have too much uncertainty, what you'll see is that typically you want to have some diversity, that you create modes with different, for example, different types of materials, because you're not fully sure yet what they will encounter, and maybe only some will come out. That then gives you more knowledge for the next generation. Yeah.
So what does the container look like that goes into the oil well?
So the one you tested with was like very hard plastic, oh no, ceramic?
Yeah,
I don't know.
Elena is the person who, maybe you can answer, who did these experiments.
Yeah, we ran the most part of the experiment in Canada, and it was very
So if you have ambitions for further explorations of oil wells, then Elena can give advice, some pre-existing knowledge to get the first experiment started as well.
The problem with the oil well was that the pump in the beginning is the bottleneck for the size. So that was a challenge. You have to be really small, so small that we could not fit in all our stuff in there. So there is still quite some challenges.
Further questions? Yes, please.
So you will see later today that the sensor that we're doing most experiments with now is like 5-6 centimeter, which for sewing systems and so on is good. If you would really want to commercialize this, what we are not doing, you would have to be smaller, like 1 centimeter. But there we are not capable yet of getting everything in there. Yeah.
Another question is that I don't understand exactly. These sensors communicate simultaneously, or just they record on a memory and then after you extract them, you just record the data from
So the idea is mostly that they record their own data. And so the most important thing is what they record. Now, because we also want localization, they have to talk to each other because they do kind of distance measurement. So they say, hello, A, I'm number B, and then A says hello. And the time it takes for them to communicate, they can measure their relative distance. So they already have to talk to each other. So what they can also do, but again, it's in the concept, we have worked it out, but we haven't implemented that aspect, is they could also send away some of their information to others. Because what we noticed in Elena's tests in the oil well is not all motes come back. I think about 70 or 80%, I don't know anymore, but a certain percentage of the motes comes back and the other are just stuck somewhere. So, or are broken, or the battery died too soon. So then, if they communicate some information to each other, they would take each other's data out and it's not lost. Yeah. Okay.
Further questions?
Okay.
So you all can sleep well with these sensors already? That's very good. I mean, the speakers will be available also at the end of the workshop during the drinks.
Yeah.
And so if you come up with new questions that are really urgent, you can also find them then and ask them the questions that you really need answers to. So let's thank Marjan once more.
Thank you.
Heel erg bedankt. Seems I'm having a bad influence on the wireless connection of the microphone. I'm going to put my cell phone away in the hope that that helps. No, must be my beard. My apologies for this. I hope it will improve soon. Is this better? Yes. So it probably is the pen that I have in my pocket that must be resonant at the wrong frequency. Never trust wireless technology. You know, that's okay. Ladies and gentlemen, what I'm going to tell you now about is what we did in this project and what we achieved. So what Marjan explained is what we wanted to achieve and how we wanted to achieve that. And now we're going to see what actually happened and what that brought us. So we're going to look a little bit at the applications that we targeted, just to explain why we chose them and why they're so relevant. Then I'll tell you a little bit about the research we did. What did we do? How did we do it? And then I'll tell you what came out and what you can get as results from our project. Because since this project was funded by the European Union, one of the benefits of these kind of projects is that the results are publicly available. Publications are open access, data, designs, everything is available for anybody that wants to use that. Then I will show some evaluation results. And finally, I will tell you how to build your own. So if you really get enthusiastic from today, and you think, I can't make it through the weekend without doing my own exploration of the sewers in my home, we tell you how to do that. Good. So, applications. Marianne already mentioned a number. When you think about it, there's many places that we cannot get into and that we cannot really know upfront what to expect. The pipelines, the chemical plants, nuclear reactors is also kind of interesting, right? Unsafe environments. Inside of people, that's something that we would also like to know more about, but the way of opening up people is not very popular. If you could have more elegant ways of finding out what's happening inside people, that would be really nice. Underground rivers, there's many applications. So what applications did we choose and why? Well, basically, we felt that we wanted to make a difference with this research. It's an expensive project. We invest a lot of time, a lot of money, and we do that because we want to have a positive impact in the end on our society. So we gave priority to addressing primary human needs, problems related to safety, like exploring water pipes for fire extinguishing. You want to know that these are intact without having to light a fire and extinguish it to be sure. Health, you want to make sure that water pipes are safe, that there's no pollutants in there, for example. Or you want to see what's going on inside people. Energy, keeping track of what's happening in plants, in reactors. And anything related to water and food, the primary needs of people. These are the things that we wanted to address as applications. But it has consequences. Because if you start from societal relevance and then look at the applications that fit these, there are no easy answers. You get into the problems that Marianne described, the chicken and egg problem, the fact that you need to optimize, and so you end up with a technology that is very different than what's currently out there. It's, well, I wouldn't say it's crazy, that's impolite, so let's call it science fiction. Right? I mean, we're really doing something very new, it hasn't been tried before, and that in many aspects is new. Very small swarms of very small evolving sensors that go somewhere where we cannot reach them, and that do semi-intelligent things and then tell us what's going on. To solve that, it's not just requiring breakthroughs in many areas, it's in fact also encompassing a large range of research areas. If you want to do this right, you need to investigate and find new electronics, very low power electronics. You need to do advanced power management. You need to find ways to implement intelligence on the cheap, on the low power, right? The instincts that Marianne mentioned. You need to have a human interface that makes this technology accessible to real people. You need to make transducers that can do, for example, ultrasound underwater or in a fluid to allow communication at a very low power level. You need all these things. So you need a team of people, a team of researchers that has a range of research areas ranging from artificial intelligence algorithms, through material science, through knowledge elucidation and storage, database design, a really wide range of people, and they need to work closely together. So we have this challenge, and on top of that, we want to make something that works for real. We don't do this to publish papers on all these individual areas. We do this because once we have explored the technologies in electronics, in software, and so on, we want to put that together, and we want that technology to be able to solve real-world problems. So it should not just be a theoretical solution. Fortunately, we found a really wonderful team of people to do this. I already mentioned the organizations that are involved, but I really would like to point out that these are the people that did the actual work. I have the honor of representing the project sometimes, but for those of you not familiar in detail with how universities work, at universities, professors like Marianne and me, we come up with nice projects and we make nice work packages, and then we find students to do the real work. And that's the case also in this project. So I would like to emphasize that even though it's in many cases the staff members presenting here, that is basically because there are so many researchers involved, so many students involved, that we could not give each of them half an hour to explain what they're doing. So we had to have people standing up front here that could summarize multiple students into a short presentation. But these are the people that really did the work, and many of them are present here, and I think they should really get the credit for all the work that they did. And this is what they did. Right? Here you have an idea of what research means in reality. It's spending time with electronics. It's spending time presenting, discussing, eating, also important. All these things. And that went on for many years, very intensive work, in all these different fields. And so what did it get us? Well, it got us a lot of results. And that's what I'm going to do in this presentation. I'm going to give you a bird's eye view of all the results that we got. And it's a lot. So I cannot spend a lot of time on each of the individual results, but it should be enough to give you an overview, sort of a table of contents of what has been achieved. And from that, you will get more detailed presentations later this afternoon, but you can also ask individual researchers about, tell me more about this, tell me more about that. Can I have this? Can I take it home? And the answer very often will be yes. Depends a little bit if it's very expensive measurement equipment. The answer might be no, but at least the design, the IP, the papers, yes. All of that is available. So, what did we do in this project? What results did we get? If you look at this is the dual cycle that Marianne explained. Right? So we have the virtual environment with the simulator, where we do the hundreds and thousands of iterations of evolution to get better mode families, better casts. Then we have the real life situation, the unknown environment, with the different physical casts, generating data. In these casts, we have sensors, we have localization, we have instincts. All of these things we have results from. But also to drive it. There's been a lot of work also that went into elucidating knowledge. Right? We want to start from somewhere. If you start by throwing things into a sewer or into a water pipe, then you can, of course, just try things. And that is fun. But it might make sense to talk to some experts first, and especially, for example, if it's drinking water distribution, to get some input on what would be good to put in there without really affecting the health of half a city, right? Which is probably good for your reputation. So getting that kind of insights and storing that in a way that it becomes available to this environment, so that we take all that knowledge, that combined knowledge, into account in setting up our experiments and running these loops, that is also an important aspect. That has to be stored in some way in a knowledge base, and one of the things that we did there is to deal with uncertain knowledge, because there's uncertainties about the environment. And so the knowledge that we have is not absolute, it's not perfect. And then, of course, there's human interface. There's two kinds of human interface. There's human interface that we make as researchers, and that allows us to fiddle with all the bits and really see what's happening. And then there's human interface that we need to make this accessible for the people that really want to solve these problems. And they don't necessarily want to understand all the bits, and they don't want to know exactly how a behavioral tree works and what the different bits in the configuration register now really do. So all of this has been done. Then we also got results by integrating all of this together and evaluating it, see whether it really worked, and documenting it. And then there's some next steps. So this gives you an overview of the type of results that we got, and I will now quickly go through each of these parts and give you a quick overview in each of these parts what we achieved. So knowledge elucidation. We developed some models for doing knowledge elicitation, and especially how to deal with uncertain knowledge. And we had some sessions with experts to try that and make sure that it really works. these results were stored in a knowledge base, and we have now a database and methods to use that to store, retrieve, and process uncertain knowledge that we have made in a very formal way available through such a database. The human interface, very famous topic. Started out, as I said, as something that allowed us to twiddle all the bits, but then quickly we found out that we needed something that was usable by many people. And so one of the students that was added as a complementary project to the big Phoenix project, Eloisa is actually here in the audience. She worked on making a user interface that is actually useful for people that are not into the details of the project, and that developed to several generations into information that's actually usable for normal people. And that looks a little bit like this. Core evolution, the fundamental algorithm, the central algorithm that allows us to do the iterations and to optimize the virtual modes. A lot of work went into building this complex software structure, into defining it, and into running it. And running it is a challenge. This is the thing that really takes a lot of computer time. You can spend easily hours or a day running these type of hundreds or thousands of iterations. Optimizing that, making sure it works well, is a big task, and we're very glad that we have this work now at a state where we get very good results. And it's really something that we keep getting better at. So the best results we got this morning at 10:30. And that's what you will see in the demo. But it's really something that we keep improving over time. But we also looked at ways to speed it up. A big part of the time that we spend in this virtual environment, in this co-evolution, is spent in simulation. In simulating what happens to modes in pipes, in containers, within fluids, and with fluid streams. And at the moment, we are doing that in a very straightforward way, and that takes a lot of time. We estimate maybe 3/4 of the time of the evolution is spent in simulation. One of the students looked into ways to improve that by also storing knowledge about building blocks. Because many of these environments we can think of as a set of building blocks. If you think about pipes, and you can think of them as sections of pipe. You can have a straight section, you can have a bend, you can have a T-intersection, you can have a crossing, you can have a tap or a valve. And each of those you can once model individually and then make an abstract model of that. And you don't have to simulate it every time. And so we did work on that, and there's results from that as well. Instincts. There was a lot of work in both working out the concepts of the best possible instincts for our modes, using behavioral trees and Bayesian networks, as Marianne explained, but also implementing them in a very, very low power way and a very small way. You see some of the results here. Then the modes themselves. We have many modes. So when you go to the demo, you will see many of them. And we have two classes. We have a class of modes that we use to integrate with the total system and to test concepts. And these modes we chose intentionally as modes that are very flexible, that are quick to build, that are cheap, that we don't mind so much if there's an accident, if there's some water leaking in there or somebody steps on them or drops them, because they're cheap and easy to replace, but they're fairly big. And they're the most of them that we have are this size. And there are many variants, because we can easily modify them and easily experiment with them. And in fact, there are even non-spherical ones, and there are ones that have small tails and so on, to see what you can do to get better results. Right? So that there's a lot of that going on. But at the same time, we know that eventually, for many applications, we need something small. Within this project, even with the 4 years, even with 3.6 million, it's not possible to develop and industrialize a set of really tiny sensors, because that is a lot more work than we can fit into this project. So what we did instead was we've identified the critical parts that we needed to prove, to know for sure that we can make these modes small in the future. And so we have electronics and transducers and so on that we now know we can make small transducers, small motes from. And you will see these parts as well. We can demonstrate that. We have built them. But we don't have all the parts that you need to make a complete tiny mote, because some parts there's no research value. Some parts we know can be done. It's a lot of work to do it. It's expensive to do it. But from a research point of view, from risk reduction, it doesn't bring us anything. So that is something we did not. Localization. We did a lot of work on localization, because when you think about it, it's really nice to have a mote that has sensors that can sense all kinds of stuff. But if you don't know where a certain value was sensed, many applications find that information rather unuseful. Right? If you have, for example, a pipe system, and you're trying to find where the pipe is leaking, and you have a sensor that says, yes, I did measurement number 7,325, and there I found a leak, but I don't know where it was. Localization is really crucial. So we did a lot of work. We found 3 methods that work. We have worked on FMCW ultrasound. That's a technology that allows us, by sweeping the frequency of ultrasound, to really measure accurately distances. There's a breakthrough combining artificial intelligence algorithms with inertial navigation to give us also accurate positioning, much more accurate than you get from normal post-processing of inertial navigation. And that's something you will also see in the demo. And we're working and have now results on near-field magnetic communication and positioning to complement the other ones. Sensors, well, you already heard, right? Extremely low power, flexible sensor interfaces. Fully integrated, can work with virtual any capacitive or resistive sensor at a power level more than 1,000 times lower than off-the-shelf components. This is a crucial thing that we needed to prove to show that we can, in fact, make the whole mode small in the future. Because when you think about it, it's not just, it's actually not at all the size of the electronics. Electronics can always be made small. Very often it's the size of the battery. And so bringing the power dissipation down is the essential thing. If you think about it, if we want to make a mode, for example, for these oil wells, you want a mode in the order of, let's say, 10 millimeters. But there's a lot of pressure down there, so you need a thick shell. So on the inside it might be 5 millimeters. How much battery can you fit into 5 millimeters? Together with the sensors, together with the memory, together with the electronics? It's not much. We're talking about microamp hours. So we're really talking about very low power. And we looked at crucial parts, the parts that take at the moment very much power. And we proved for those that we know how to miniaturize the power dissipation and the electronics. So that brings us to an interesting question. We have all these results. It's just really nice. We have all the pieces of the puzzle. But can we make a puzzle? Remember that we started out saying that we don't just want to do this research. We don't just want to publish that we have a nice algorithm. We don't just want to publish that we have a nice chip or a nice transducer. We want this to be useful. So we had to put the pieces together. We had to integrate the hardware and the software. We had to build setups to test this in. And that's important because you can, of course, take a really unknown environment, but then you don't know whether the answers you get are correct. So we need an evaluation setup where the environment is unknown to the system, but it's known to us so that we can check whether the answers are correct. And we had to work out ways for us to work together. It's non-trivial. Working together with enthusiastic people is always nice, but if you have people from very different fields, it takes some time to get used to each other and to find out what we mean and how we really get our results to fit to each other. And so we developed, and it was also one of the results from this project, new ways of working in these type of teams together. By the way, also for your information, one of the other things that is publicly available is the presentations you see today. So we will also publish those. So the evaluation, how do you do that? Well, the first try was actually a lot of fun. We said, let's make the simplest possible setup. We make a straight pipe, 5 meters. We put a T-junction somewhere. We don't tell the system where it is, and we have the system find the T-junction. That was the simplest we could come up with. When we built it, and many people were involved in making this reel, of course such a pipe has a start and an end. Right? The start we put a big tank of water. The end we just had spill over in a small children's swimming pool. That worked, but then you need to retrieve these motes, right? Because they just float in the swimming pool and they need to go back to the start of the cycle. Well, what do you do at a university in a case like this? What you always do, you get students to do it, right? So we had a lot of students fishing out motes from pools, and we had a project called the Pool Party, and we had a project called Pool Party 2, where they did these experiments for us. Nevertheless, it's an inefficient setup for two reasons. One is that you spend a lot of time retrieving motes, but they go very quickly through the pipe. So the efficiency, the time that the mote actually does something useful is small. The other problem is it has to be outside because it's too big. And that means that in the Netherlands, somewhere around October or November, you stop doing experiments because the whole thing freezes. So we went to the second setup. You see here a very advanced design where the motes actually make infinite loops through a set of pipes. And there's even junctions in there, so they don't always take the same loop. And this was realized also again by students. And this is something that you will see in the demo in a few minutes. And here these loops, these balls make really long runs. We can put them in there for, well, as long as we want essentially. And we get a lot of data. So in a very short time, we generated hundreds of megabytes of data from this setup. And this is what you need to really train your system. It has some nice features, like it has random paths. It works at almost atmospheric pressure. It can do reasonable speeds. You can see that later. We have a controlled way of getting the motes in and out, which is also really nice. That's through these vertical pipes. It's modular, so we can easily change it. It's transparent, so we know what really is happening inside, and we can check whether that fits the data. And it's using off-the-shelf parts. So you actually can build that this weekend yourself. You just go to the Gamma or one of these other stores and you buy stuff like this. And you can actually play around with your own modes. The other nice feature compared to the previous one is that scientists and the environment remain mostly dry, which was definitely not true of the previous setup. Still, it's not 100% fail-safe. There's always some water dripping, and we had a small accident with a water pump that we don't discuss anymore. Yeah. And this is what you will see in a few minutes. Just to give you an idea what happens in these pipes here, you can see how this actually works. So you see here the water floating, and you see this T-junction, and you see these balls floating by, and sometimes going one direction and sometimes going in another direction. I also want to point your attention to these features. These are the shoes of the cameraman. And this gives us data. We get accelerometer data, we get rotation information, and we do post-processing to make this output make sense for normal people. So you can, for example, see what all these accelerations and rotations do to the position of a device. And then we document this. This is always, well, maybe not the most popular part of a project, but it's always the most important part. And so we have a lot of publications. Currently we are around 40 publications. There's another 10 or 15 coming. We have presentations, workshops like this to explain to people what we've done and to try to encourage them to think about whether it can be useful for them. We have movies, we have pictures, we have data, we have designs, software. All of that is available, and that is available through our website. And now that the project is at its close, we will, in the next few days, increase the data that's on the website, make more and more of that public. So at the moment, we have the formal deliverables of the project on there, the formal publications, but we will also clean up more and more of the internal design documents and make them available to you as well, so that you can also use them. So what are we going to do next? Well, we have this technology, this project. And we've done this project, we've explored the technology, we have research results. We validated it in these setups, and you can see in a short while that it really works. and use that result of the validation to further optimize the research. But it doesn't stop there. One of the things that we're going to do is to continue this research. We're really excited about the results we're getting here. And we think there's more applications and there's further development of the technology possible to make this more useful and to increase the range of applications that we can cover. So this research path will continue, and there will be many more projects where we, for example, look at different applications, but also at different kinds of technology. For example, thus far we've looked at just sensors. But just think about what you could do if these things were not just sensing. What if these things could do something, if there would be actuators in there? It's really nice to have a ball or a swarm of balls going through a water pipe system and say there's a leak here. Wouldn't it be much nicer if one of these balls could take some chewing gum and close that leak? Maybe not chewing gum, but something much more scientific. So that's one direction where we're looking at. Of course, continuing the direction of smaller and smaller balls. Ultimately, we want to go to balls that are so small that you can use them in just about any application. So that's the research part. Parallel to that, we are looking at ways to make this technology useful and used, exploitation of the results. So we're working in what's called the Launchpad subsidy in a cooperation between some of the partners to turn these results into a technology that really will become available for anybody to use, where you can order hardware, where you can order software, where you can order services to inspect whatever system you have. And that is something that we want to base on this technology and then develop into a more industrial phase. Because, again, I hope I'm not disclosing any deep secrets of a university, but results that come out of student projects are not always at a maturity level where you can use that in an industrial setting. So we think there's some additional work needed, and that's what we will do in this branch. And obviously, a lot of these results will feed back into the research, and a lot of research results will feed back into further exploration and exploitation. So, where are we then? Well, we have outreach. We are at the end of the project. We want people to know about this. That's what this workshop is for. We're maybe a little bit unusual in that we want to give most information about this project at the end. I know in academics it's more usual to make a lot of noise already from the start of a project. But we think, as real scientists, that's important to first have something before that you start shouting about it. And that's what you will see over the next weeks. So from this workshop, there will be press release, there will be more and more documentation available, and you will see more and more of this project on our website, in newspapers, and so on. We will continue the research, advanced applications, advanced technologies, and we will industrialize this. And there's some announcement in that area in the near future as well. So look for the word SMARBLE, and if you see that, then you know that that's related to this project. So finally, for these people that really want to work this weekend building their own swarm, all the parts that you need will be open source. The documentation, the designs, the big balls are all based on off-the-shelf components. Anybody can buy, even in single quantities. They're cheap. The firmware design, the housing, we will release the mechanical drawings for the housing and the firmware for the balls. We use, at some places, commercial libraries and tools, because we can't do everything from scratch. But at least the things that we did will be publicly available, and you can either use the same libraries and tools, or you can adapt it to your preferred libraries and tools. Unfortunately, there's one exception, and that is the IC designs. Unfortunately, IC designs, if you fabricate them, you need to use libraries from the foundries, and for those, to get access to those, you need to sign NDAs, and that means that we're not allowed to release the full design database. But we do disclose and publish the design information, but not the full design database. If that's a problem, we can always set up follow-up projects and see how to improve on that. So if you want to do this at home, what do you need? Well, you need a fast PC, you need a graphics card, you need Linux. Most people have already a lot of that. You need to make a PCB in some way. The designs of that are also available. You need to buy some components, just from Conrad or Farnell or whatever. You need to solder it together. You need to test whether it works. Put the firmware on there. And you need to 3D print the housing. And then you put it together and you have the balls, the same ones that you will see in the demo. It costs very little. If you have the PC, it's less than a few €100. So this is really something people can do at home and that you can experiment with if you want to continue this research in your company, in your university. And we're quite happy to work together with you to make that possible. So where does that bring us? Well, we are now at the end of a project that started from some relevant but difficult application where we really tried some science fiction ideas. The idea of having swarms of sensors that evolve over time and become better at what they need to do and tell the user the answer to his questions in a way that's understandable for a normal person, that is science fiction. But we have the technology now. We have achieved these targets. And now we want to continue. We want to explore new technologies. We want to industrialize it. But we also need your help. And that's one of the reasons why we have this workshop. We think that this technology probably can be used for more than what we all realize at this moment. So if you have an interesting application or you have an interesting problem and you think that maybe some of this science fiction could help you, could be applicable, please let us know, because we really are very eager to do new research to adapt it to exactly your problem, or to help you build your own swarm, or to help you do your own experiments. Because that is, in the end, what makes us happy. That brings me to the end of this presentation. Thank you very much for your attention. Are there any questions? Yes?
I hope you don't perceive this question as offensive.
No, you need to do a lot more.
There was a time that both you and I worked at Philips.
Yes.
And about 15 to 20 years ago, there used to be a project called SAND. Maybe you remember.
I remember, yes.
Yeah, indeed. That had, when I compare the size of your PCBs, they didn't shrink.
No, true.
But in the meantime, let's say the computational power increased by more than 2 orders of magnitude. So
true.
How did you exploit it, and how can I see that?
Okay, so that is exploited by not the part that you will see in the demo. The main part of the demo, the big balls, we designed them using off-the-shelf components to validate the concept, because that gives us very quick development, it gives us flexibility and so on. I think you also remember, you know probably better than I, how expensive it is and how time-consuming to make a chip. And so for the large part, if we could avoid that to prove the concept, we avoided it. But we still did IC research, and so yes, I remember the grain of sand, and I always carry one with me, so we have ICs this size, right? And so you will also see in the demo that we have the critical parts of the electronics, we have this small, and part of the research, one part of the research is really making the balls this small. The problem is not so much the electronics, because we know that can be done. We have done it. The problem, and that's something that in this Philips project from long ago we probably underestimated, is how slow that battery technology develops.
That's true.
IC technology is great. We're complaining because more slowing down. But if that's bothering you, take one look at the roadmaps of batteries and you feel a lot better.
Okay.
Further questions? No? You're all eager to go and see the demo? Then let's do it this way. Let's, for this half of the room, so from this side of the corridor, let's do the first round of demos. Where did Dirk Jan go? He escaped. Okay. So then Jan Haag will walk with you to the room and to the building where the demo is. And I will stay here with the other half, and we will switch then halfway through, because the demo is in a room that didn't really intend to accommodate this many people at once. And I really want you to have a good look at the demo and play with everything. And if you want, you can even put your hands in the water. Thanks a lot and enjoy.
All this information we will need to initiate the environmental model, simulations of the environments where the balls can go inside. And as you already heard before in previous talks, our system would suggest you to use black balls, which have gyroscope, accelerometer, and magnetometer. I don't go into the details because again you've heard about it. And these balls are suggested because they are available, they are relatively cheap. You see that many people are starting to use them already in many applications. And there is some already knowledge building up on the balls. So, and we say then proceed. We have some model, we have some balls, and now we can initiate the system. But I should apologize, I have to start the pump first. And it's a little bit loud. Because I will prepare the balls in meantime in one more to send it to the system. And then we will show
send it through. Yeah, send it through.
What's happening louder?
I cannot allow myself.
What? You mean interpreting the mic?
So what's happening?
I'll get closer. So currently the suggested firmware that is the suggested interface is through the remote. It's closed and should go around.
It is research for that. That's why
What we'll do now is just reading it out. I want to data this. I have to do it by hand still, and a little bit fluid of algorithms in the program. In the meantime, Ganesh, the guy with the yellow shirt, has a demo for you on how the ultrasound works. So you manage to squeeze in there, and one half that doesn't squeeze with Ganesh might go to Jago, the guy next to it. That helps.
So half or no?
Yeah, half.
That's better.
Right? Does that fit?
It's quite close.
Okay, and maybe all together.
That's better. Hello. During this time, I will show you what's happening here. As you may remember from the presentation of Marian, one part was the communication and ranging between the sensors. Here I am going to demonstrate an example of it. I mean, please do not mind the size, because this can be made small, but the small black pieces of silicon that you see here are actually our chips. So here, actually, one side mimics as a sensor node, let's say, that is going to answer. And this sensor node, this side, is the one that's going to initiate a communication. And the system that I propose is work as follows. The one that wants to perform localization sends a hello signal to the environment. And the one that nearby means that receives this signal above a certain threshold, responds back with a frequency modulated signal. And the initiator will chirp this received signal and its own built-in chirp generator, and then resulting a data frame will be saved in the memory. Here, as a memory, I am using the FPGA's memory, and then I am reading out the data that is saved in the memory, and in the MATLAB, we will post-process it and find the distance, and the distance will pop up here. So right now, I just randomly place them. Actually, you see around 7.5 centimeter distance between the sensors. So now, when I use the computer, I will just send a start flag that starts the, let's say, a communication, and then we should measure the distance. Now it sends back, it receives, saves it to memory. Oh, and now we couldn't measure it somehow. This is demo effect. Let's retry. It should do something. Maybe I forgot to refresh. Let's retry. Indeed, now it works, and as you see, it finds the maximum frequency that's received and calculates the distance and pops up here at 7.5 centimeters. Now the frequency response is here, not clean, as because the natural habitat of these chips in our labs where everything is shielded. Right now we are hearing most of the 50 Hertz, but it still works. So then let's try another distance, for instance. We just need to refresh these guys. And maybe one of you can set a random distance or this one? Yeah, these two together. All right, so let's measure. So something around 17 centimeters is expected. Let's try. Sends the signal, receives back. And indeed, 15.8 centimeters or 16 centimeters might be by error. Yes, indeed, 16 centimeters was the correct distance, sorry. So this is actually works better than my side. So this is, for instance, how sensor nodes perform ranging and communication between each other to find the relative distance between them.
Quick question. So this is in principle, in fact, a radar system based on ultrasound.
Yes.
So it's the speed of the sound. So if in the real life you have different environments, you have to have that as part of your expert knowledge, the speed of sound in that medium to be able to calculate that.
Here the error, range of error is twofold. One, the transducers have limited bandwidth, so this actually introduces an error compared to radar systems where you can reach gigahertz. The second, you need to know the speed of ultrasound in a certain medium. So in air, it is 300. But in water, actually it also depends on the temperature, for instance.
Yeah.
1450 or 1500, etc. But this is kind of an information that you solve in the post-processing part.
Right.
Because you have temperature sensors, you measure the temperature the moment that you perform the, let's say, ranging.
So there will be a stamp on every measurement, that measurement was measured at maybe a certain time, a certain temperature, or that.
Exactly.
So that will be put in the database.
Exactly, because on-chip range processing is not done on-chip.
No,
we just save data frame to memory, and then we take the FFT, and then filtering, etc. We find peaks. There are magics going on there, but it's not on-chip. It's the part of the project. It is post-processing, which will be handled in that phase.
What are the typical distances you can measure?
In air, I characterized until the 2 meters, but now I have a limited space. And it is mostly depending on the transducer that you use, as I said, the bandwidth of it. and the strength of your transmitter. So you can reach in the large instances if you want, if you have enough power. Or, by the way, it is also need to mention that this is just a demonstration for air. It is meant actually in water, where the attenuation is 140 times less compared to air. So distance in 1 meter, actually, if you predict the received power in water, even kilometer can be reduced. So distance can be actually quite improved in water environments or fluidic environments. So that would be my demo.
Is ultrasound actually the sensor of choice if in the end you want to make it very, very small?
Actually, that is the reason. For instance, there is also near field technology used in the project, but the size and the power is a concern over there. In ultrasound, in theory, you can make everything so small so that you can even put this inside the human body. That's the real aim.
We need to move on to the next, because the next group is already coming.
Thank you so much.
Yeah.
Yes. Okay. Then we will continue with this demo. What you see here is the chip that is basically the whole sensor part of the Phoenix project. So, what were the requirements? It had to have multiple sensors that are interchangeable. This is what you see here. Here we basically plugged onto our PCB a few sensors. We could theoretically plug this off, plug in a different sensor, and be on our way again. It had to be low power. I think you can see the screen clearly enough. But here you can see it's below a microwatt of power used at this point. What else does it have to be? We also have to make it adaptive. So here at this moment we have put a quick demo project here where we basically, if the light goes out, the accelerometers start sensing. Now, if the accelerometer starts sensing, there's more activity. They have to be stored into the memory. It's going to take more power. So, if we, for example, if I close off the light, you see the power going up because the accelerometer starts sensing and so on. This is only the measured power of the chip. You also have to put on a memory after that also consumes power. So it will scale more when you put a memory behind it. Inside this chip, this adaptive behavior is created using behavioral trees. These behavioral trees, as seen in the presentation, they can be evolved to create a better behavior. They are then translated into if-else code, and this can be processed by the chip with very low computational power. So this is our implementation of an instinct. Questions? Then we continue with...
Yes. Yes. Well, nice timing here. Perfect. I just very quickly processed the data we got. For those to whom that says something, we got an F1 score because we've learned on the pipe loop what are bands, what are junctions, of 0.88, which is actually not pretty good. What you can see, but sorry, we did not get this big screen working, is the difference between the prediction and the real thing. And for the people in the front, from the people in the front, you can probably see that these are pretty close. The screen, so the two are very similar in where they were. The only magic trick that we did here is that we fixed the scale, because for that you need flow rate. So those are fixed. But other than that, identifying bands and T-junctions, it did on its own. So it's a reasonable result. This we would then take into the loop and make a next run with the optimized instincts, but we will do that with the next group. Sorry, yeah, it looks exactly it looks exactly the same. If it all works out, the results are
No, the results are the same, except the power used is less. So there's a number that goes lower. But given time, thank you for your attention.
Okay, we as group can walk back to the coffee and to the drinks, and then the other group can take over.
Thank you very much for your attention. No problem.
Yes.
All right.
Line of sight.
You would be able to split up and get there. Two people there, and I can.
Which is not a very funny.
Welcome to our little test and demo setup. What we have here is a completely unknown system, of course, which we built ourselves. But the idea is that here we can prove some of the technologies. What we want to know basically here is, and it's a question we actually got, is where are, for example, old extensions, so old junctions on a pipe system. So hence you see this thing sticking out. So we happen to know there is one. But Elena will now basically start the inspection by inputting the data that we do know into the export system. The export system will advise you on the first generation of modes to use. So,
so especially if you remember all the talks you just heard in the morning in the first half of the day, right? If I am a researcher and client, I want to know my system, right? It's not like we don't know anything. If I want to study pipelines, I want to study pipelines, right? So I'm coming to a group, for example, or I'm coming to you and saying, okay, I want to know what is here under this carpet. I know that there are pipes, but information is out there. I only know that I can put something here, or I'm putting water inside here, I'm filling it here with water, and water goes out here, right? So like that, we are starting the inspection. This is also just a mock-up, particularly for this demo, also not completely worked out. So as I said, we know that it is a pipe-like environment. It's not an underground oil reservoir, a strange picture and so on. It's already much bigger. So we choose the pipeline and we want to know the shape of it. We want to map it. We are not interested to optimize the agents which will there because it's not my goal. I'm just following the pipeline. As we know, we're asking if what is the distance between two, what do you know about this system? I know that the distance between this point and this point is 1 meter. That's very sure. I know the flow speed because I'm running it with my pump, which we bought some time ago. There are specs that we started with 23 liters an hour, 23,000 liters an hour. So it's quite powerful pump for the system, which we can discuss that part. And of course, I know where put bolts again. What is the diameter? We put this information inside. And I like to know what it is PVC, maybe material, different material, but it is PVC. And we can put that. So we go to the next step. And like that, we already have our information to start the first evolutionary or electronic system or the complex computational stuff. So we have some initial steps for the model of the environment. And as you know also from the talks, these sensables were already becoming quite known. They are used in different applications. So it's not a surprise that the system is recommending to use our sensables, especially because their size is also quite superior. They're only 6 centimeters in diameter, can be done into the pipeline. And this is a suggested agent for that job. And like that, because it's fun,
Yep. So, well, Elena prepared the mode that the system suggested. I'll start the pump. And actually, we're using the second generation mode. So we already did one for the first group based on this information, and now we'll run one with the with the new instinct. And I dare to tell you the score of the last run was 88% F1 score. So hopefully we'll improve on that. That's what at least will happen is probably that the power will be slightly lower. But that we'll see after the run. Hopefully. Yes? Almost? So after the run, we take out the motes, we read it out. I have to play to couple some algorithms together to get the algorithm. So there will be a 5 minute me being a computer. During that time, Jonas and Jaro will present their side demos on the actual sensor development in China. So if all goes well now, and we have the correct output. At least it didn't get stuck. Well, we know now that the system has no holes smaller than 5 centimeters. That's the first bit of information.
How often did it travel through? Once?
Now we did one run, yes. Yes. Now there's some tricks you have to play with flow straighteners and things, so you cannot making it continuous is a bit tricky if you want to do it. So I would hand you over to Gönich and Jaro in the corner. I know it's a bit crowded there, but please.
Please, we may need to screen.
I can see the
Hello.
Well.
As you may remember from the presentations, one job of the sensor nodes is to communication and to perform ranging between them to find the relative distance between each other. So here I try to make a demo to show the feasibility of this system using our integrated circuits. Right now you see here two sides. One side actually acts as a wake-up receiver, and the other acts as the main receiver who initiates the communication or who wants to perform ranging. Here we see actually 4 ICs. These black, those are our silicon pieces. 2 of them are receiver, 2 of them are transmitter. One is for the initiator, the other is for the wake-up. And the system that I proposed works as follows. The one that the initiator sends a hello signal to the environment, and whoever is around receives it. If the signal is above a certain threshold, it answers back with a frequency modulated continuous wave. And the initiator receives this answer back and then multiplies it inside. And then this data frame is digitized and saved into the memory. And then this information will be later on processed in the post-processing part where we take the FFT, etc. Here, I use the memory inside the FPGA to mimic this operation. And then I transfer this information to MATLAB, and I do the post-processing also. So we will see the distance calculation online. So let's try. So here, actually, the generation of the signals and processing is all online with the hardware. I just, from the MATLAB, I say a start signal, and then the operation starts itself. So, from the previous demo, I know the distance, it was around 16 centimeters. So, but I ask one of you to just play and then set a random distance. So let's see if we can measure also. You just need to move it random, let's say.
Both, yeah?
Both, yeah. All right. So leave distance is around 22 centimeters. By the way, accuracy of the system is 1 centimeter, sorry. So I'm roughly calculating 22. So let's say, let's start the operation. says the hello, receives and answers back. And the measured distance pops up here is 21.67 centimeters. Close match to 22 exactly. So if you want to repeat, we just need to refresh FPGAs, otherwise they remember all settings. And then if you want, let's make it second run. So I just arbitrarily move them around 13 centimeters. Let's run it. Indeed, we measured 14.16 centimeters. So that's how communication and ranging works.
But you have to know the speed of sound in a medium.
That's kind of the limitation of accuracy. Actually, two error of source of error. One is the bandwidth limitation of the transducers. This actually creates a ranging inaccuracy. The other is the unknown speed of ultrasound, or it also depends on the medium. However, this problem is solved in the Phoenix project because we are processing the data offshore. So where we have actually sensors, where the temperature is measured, for instance, etc. So we can actually estimate also the speed of ultrasound in a given medium. But of course, we have to know the speed of sound because it's actually two ways. So
And another way this is being addressed is by the fact that we have multiple ways of doing positioning. And so we do this with ultrasound, but we also have near field magnetic. And there the speed is different, is not correlated with the speed of sound. In fact, it's so high that it's almost instantaneous at these distances. So by having both measurements, we can get a reliable indication of the distance, and we can get information about the speed of sound, because now we have two equations with two unknowns, and that gives us additional information. So in principle, it's solvable, even if you have a non-homogeneous medium, right? So some sand, some water, some oil, some whatever, then it still will work. But that's the theory. Reality, of course, is always, we need more experiments to verify how well that really works.
No, there's no relation between those two.
This is something that will be inside these balls, and they will then talk to each other to find the distance between the balls. And if you have enough of these distance measurements, you can find the locations. So that's the relation. But we have a setup here. We do this normally underwater, but the aquarium that we use for that is not so easy to transport. So here we do it now in air. But normally it's in water. It's built for underwater. And it's also built for being inside these balls. That gives some additional challenges because these transducers have a fairly narrow beam. So one transducer doesn't do everything, but that's where Sina comes in, because he has nice transducers that can do a lot better. So there's a lot of research going on to solve all these problems, and we do have solutions for all of these things, but not yet in one tiny ball yet. Next workshop, hopefully.
And how do you decide when another ball is present? Because if you keep it running all the time, then it will probably cost a lot of battery power.
Actually, it is due to cycle. So you activate your transmitter when you want to perform the ranging. So in a sense, it is due to cycle. And only active power is the always on power of the receiver, because it has to listen.
But that's where the wake-up receiver comes in.
And that's where the wake-up receiver comes in. Currently, it consumes 1.12 microwatts. And our new generation ICs, that is not here yet, but then we reduce it to a nanowatt few minutes.
Okay. These are just automotive parking sets?
I just found them on the Farnham. No, nothing special.
Yeah. But the special ones are the ones from Sina, right? So that
yes,
the ones that you saw in the pictures.
Yeah.
All right. Thank you.
Thank you. Let's continue with the sensor demo. So,
who's er één watching?
Laptop mic.
is working?
Yes, I think it should be fine.
Should be fine.
Okay.
Yeah, it's working.
Okay.
Ladies and gentlemen, could you please take a seat? We're going to continue our workshop program this afternoon with the second talk. I hope you enjoyed the demo. If you have any questions about that, please feel free to ask during the drinks afterwards. But now we're going to continue with some more detailed technical presentations about some of the most exciting parts of our technology. And the first presentation will be by Martin Andro, and he's going to present the sensor nodes and the instincts. So Martin, can I give the floor to you?
Yes, thank you. Thank you for letting me talk in this workshop. I'm like some kind of a pure product of Phoenix project. I mean, it helped me a lot during my early career, so I'm really thankful to all the people that gave me the opportunity to be in this project. So I want to go a bit more into details about how we implement this instinct. So Marianne said that she gave all the ideas behind this, but let's say we want to maybe understand a bit more and a bit deeper how from the hardware perspective and the software perspective this goes together. And this is the title of my presentation, so co-evolving hardware and software. I don't think this works. Okay. Right. So let's go a bit into what we sort of know already. We know that we have sensory nodes. We know that these nodes can sense, can store data, can communicate. We also know that these nodes are very small, millimeter to centimeter size. So they have a very, very low resources. Okay, so Peter will go into details about how these sensors are really made and which kind of circuits we have in there. But for now, what we want to do is to give them instincts. And instinct means, okay, when you are human, when you react to something, when you instinctively react, it means that you're not thinking about it. You just have a reaction without really spending time thinking about it. And it's translated to the circuit to reacting without spending valuable computing power or time or anything. So that you can really adapt to things that are in your environment and it doesn't cost you a lot of time and a lot of power. And in a nutshell, the idea of the project is that we co-evolve at the same time the software and the hardware. So the software tunes the hardware, so it will tell the hardware how to behave in this particular environment, and the data that we gathered with this hardware will be used to also improve the software, and then we will repeat these cycles again and again, and this is what we refer at the co-evolution. So that's to give you a bit of context. So in this talk I will give some generalities on how we adapt circuits and hardware systems, just to give you some let's say basics or the terminology that we use. And then I will get into details about this proposed instinct-based adaptation, so giving you the general idea and then how we really implement that in terms of electronic circuits. I will go through two case studies. One is like kind of a toy example to have a grasp of how it works, and another one is on the adaptive sensor interface, and it's a chip that has been measured just recently, and we have preliminary results here. And then I will conclude the talk. So how do we adapt circuits? Well, there are basically generally two techniques. The first one is called offline adaptation. The idea here is that the circuit will know what to do in which case before its lifetime, so before we put the circuit in the field. For that, we will train and build a model, so through software optimizer, for example, or different techniques. And we will take into account all possible conditions. We will try to find out how to tune the circuit for all these possible conditions. And then we will embed on the circuit only an execution of this, let's say, behavior of this model in, for example, the form of a lookup table. So we will sense data and then deduce which are the current conditions. Then the lookup table will tell us how we should tune the circuit to better react to it. So it's very interesting because it needs few resources on chip, only let's say a lookup table or a few elements, and you can build a model with a lot of resources because this model is built offline. It can be on computers, it can be on servers, all of different things. The problem is it's not really flexible. So you build a model and then your circuit goes and that's it. So in terms of flexibility, that's not that good. So of course, what you could do is to embed everything directly on the chip. And in this case, you would say that the circuit will decide what to do in which time during its lifetime. So then you have to develop some kind of online strategy. You need to embed it. You need to know what are the rules that you want. You need maybe to even train sometimes the system online. So it all seems very interesting and it's very flexible. It can be generic, so you can do a lot of different things. You can adapt to really changing conditions, but you need a lot of resources on chip, at least some fancy processor, some DSPs. So it's complex. And if we go into the details of Phoenix itself, we have resource scarce circuits. We have circuits with megabytes of memory. We have circuits can contain lookup table with a few values. We don't have, let's say, full processors. We don't have anything like that because obviously it will consume much more and you would go into the environment and after 1 minute or two you would be dead because you don't have any battery. So online adaptation is, let's say, completely out of the scope. But still we would like to do something. Still we would like to say, okay, I just have a few settings. I know I don't have that much. Plus I know that the settings depend on what is the current task, what is the current condition, and more importantly, what is the current environment where my circuit will operate in. So the principle of the solution that we propose is this collaboration between the software and the hardware, and this collaboration between offline and online adaptation phases. So what we do is we are going offline. We decide, okay, the circuit might do this and this and that. We implement it, the circuit goes through. Then we see what we can do. So is it good? Is it better? Maybe we run out of battery too fast or these things. And we will repeat this loop again and again, and this is the challenge, and this is how we want to solve this challenge in Phoenix. So how do we do this instinct-based adaptation? So again, the key idea is we want to learn online tuning rules, so tuning rules that the circuit can follow when it goes into the environment. But we want to design them offline, because we don't have the capability to embed it in the circuit, mimicking biological instinct. It means the circuit should just switch between settings. And so we encode the online circuit behavior genetically. We put in the genes of the circuit before it goes. We say you will do like this, you will act like this. And then the next generations of the circuit, as let's say species or humans, will get different instincts. So they will get better and better at doing certain things. So essentially, from the circuit perspective, there's a front end. So for example, a sensor interface or a communication block. We have sensors, we measure some operating conditions, and then the circuit doesn't spend a lot of time. It's just said that, these are these conditions, I should react like this. And it's tuning with some tuning knobs, the circuit. So those knobs can be the power of the receiver, the power of the transceiver. They can be how many sensors you use, how fast you sample. And the idea is that since we don't have a lot of settings, then we want to pre-optimize everything as what we can before. So we have different clusters of conditions. We have different values that the tuning knobs TK can take here. And then we want to be able to have different clusters at different positions and to know this a priori, because a generic case will not work every time. And so this is realized with an optimizer that is using an evolutionary algorithm. And the principle is that this algorithm will take the performance of the circuit, and the circuit is modeled. This model is, let's say, performed offline, so it's not, let's say, there, but the key thing is that we consider the operating environment in the loop, because we really want to do something considering that particular environment. And so there are some measurements that we can take from different sensors in the circuit, and we measure what is the performance, what is the power that has been consumed in this case by the circuit, and then we understand how to tune the circuit, both from a static point of view and from a dynamic point of view here using the instinct. And then the loop and the whole adaptation works as follows. First of all, we have this offline adaptation loop. So One of the key part here is that we have a simulated environment that is available. Probably you saw it also in the demo. We have some models that are modeling how the circuit behaves in this environment. And then we will optimize for different constraints, maximizing performances, minimizing power. That can be, let's say, different things. So the evolutionary algorithms will just, let's say, go through how you can tune the circuit and what you can do. And then you go inside the environment. And here now there is like a real environment that is more or less accurate depending on the knowledge that we have from it. And then we see what we get, and then we launch a new adaptation phase, a new optimization phase, and this phase will happen again offline. So if we go a bit more into details about, let's say, how we implemented it, basically the idea to save power is to say that for your circuit, it's not always important to be very accurate. Sometimes there are some areas where you don't need to be accurate. And in these areas, you should save power. So that's what the software is figuring out. Where it is important to sense fast, to be accurate, when it's important to stop, to be lower power, because in the end, it will not matter what you know from this area. Maybe you know already something from this area, so you don't want to know more. And if we have a snapshot of, let's say, how the circuit is designed, we have three main parts. So we have one part that is the sensor interface. So we are gathering data from different sensors. We have a communication part when we communicate through ultrasound. And we have a part dedicated to data processing. So what we do here is that we gather data, we compress data, and then we store it into the memory. Why? Because the memory is small, so we need to find a strategy to store the data as efficiently as possible. So we need to find out what to sense, when to communicate, and how to store the data. And this is what the instinct is doing. And so there will be this zone detection method, both for the communication side and both for the data analysis side. How it works is that we will pre-optimize these zones through the evolutionary algorithm. So it will know, yes, this area is interesting, this area is not interesting. So, and once the circuit is running on chip, we will gather data, we will analyze this data that is gathered by the instinct block, and then we will set up the circuit and configure the circuit accordingly. So it will say, we are in zone number 1. That's a very important zone. Like, you have to sense a lot. You have to communicate a lot. I don't know. We are in this zone for communication when there are a lot of agents around. Maybe it's better not to communicate that much. Those are these kind of rules that we will to set up. And inside this instinct block, there are several key things. The first one is a lot of signals are coming. A lot of parameters can be measured. So of course you have to extract the best features from these parameters. And so you select which are the interesting signal. We use here signal statistics. For example, the mean value of a sensor measurement, the variance. We can use the signal strength, the signal to noise ratio of a communication. That can be different things. But first of all, you extract these features to have really a big grasp of what is your signal about. And then you will transfer this to a behavioral tree. I will come back to the Bayesian network later. So essentially, extracting these features will tell you in which zone you are. Are you in zone if it's important or not? And basically, the circuit will have a behavioral tree instead. So it consists of essentially different branches of actions and conditions and actions. So if something happens, do this. If something happens, do that. And this has been pre-configured, and that has been embedded in the chip. And this behavioral tree depends on a lot of parameters. It depends on the environment, the conditions, everything. And this is what the evolutionary algorithm outputs. And then, of course, once you know in which zone you are, you need to select the right data to configure your circuit. So you apply what the behavioral tree is telling you to tune the circuit. And this behavioral tree is encoded in the form of a lookup table. We have also worked, I will not go into details, but we also worked into another part, which is basically, instead of having a clear idea of which are the zones, maybe we can be more clever. We can use machine learning algorithm, specifically Bayesian networks, there are probabilistic models. So here, the idea is to say, maybe I'm in a zone or I'm another, but you want to have a probability distribution of in which zone you are. And depending on this probability distribution, you find out something. So I'm sure that I'm in this zone. I'm sure that I don't know that much, for example. That can be different things, but that's, let's say, an optional part, and we worked on possible applications on this. So, of course, we have this for the communication part, where we measure, for example, signal-to-noise ratio, interference, and then we detect what is the current zone, and we apply some settings. And we have the same block also that would be here for the data analysis. So those are similar implementations, but they have all their constraints. And, of course, there is a controller that will make the scheduling of all this instinct. So that's the general idea. Now let's see a bit how it applies to some case studies. The first one is, let's say, to give you a grasp of how really and physically it works. So it's an ultrasound communication circuit. It's composed of a transmitter that is here. There is a receiver on the other side. And part of the work is also to model what is the environment, meaning what is the channel that we are expecting. So what is the noise, what is the distance between nodes, the type of attenuation, the type of liquid, all these different things. And the circuit has tunable parameters. So what is the transmission strength when you want to send a signal? What is the sensitivity that you should have in your receiver? And the basic principle will be how to adapt the transmission strength of your circuit depending on the distance when you are from the other node with whom you are communicating with. So let's apply this. Okay, so first of all, as I said, we have this optimization offline. So we will throw the nodes into some kind of environment that we have modeled. So this depends on the application, of course. We will come with some, let's say, configuration for the circuit. And what we can say here is that, for example, as a simple example, the instinct is the strength with which you want to answer a message. So this is what is your instinct here. There is a node broadcasting a message and you want to answer. And you want to answer with, let's say, low power. And then you encode this behavior into a lookup table. So essentially, it will tell you what is the voltage that you should put in your transmitter depending on the signal-to-noise ratio that you receive. And you can parameterize all these zones in there, and which are the thresholds and which are all the values that you can use. And of course, then there would be a part when you actually see what it does, okay? And see if your objectives are satisfied. Maybe they're not satisfied in the beginning, so you will do it again. But that's generally how we apply it. And so we have here, for example, I have examples with two environments. One that is, let's say, very simple, consisting of like almost only like a straight line. And another one with bends, pipes of different bends and different sizes. So that's a bit more complicated. And yeah, just to give you an idea, we compared different approaches. What do we do if it's non-adaptive? What do we do if we fix manually what to do in the circuit once and for all? And then we go into the two environment and we see what it gives. So essentially, of course, if you have non-adaptive behavior, you will somehow transmit a lot of power. If you do it manually, you would kind of, for example, split into equal clusters of signal-to-noise ratio that you receive. But what we see is that if we use the evolutionary algorithm, it actually finds a very different split between the zones. And more importantly, that's what I want to point out here, is that for different environments, it really comes up with different splits between the zones. And that's what is interesting. Let's say the general results is maybe some kind of a toy example, but really the behavior is there, so that different environment means different zone. And for example, the second environment, the nodes stay actually in the simulation very close to each other, closer than we would expect. And so that's why you see that quickly you can say lower the transmission of the transmitter, and then you will see that actually you gain quite some power. To give you numbers, we have compared it. We take randomly a node that goes inside this environment. We measure this power consumption. We see that sometimes the instinct-based method can really benefit, up to 45%. In this case, again, it's just to see the trend. What we see is that every time that we do this adaptation, we gain some power. Sometimes it's a bit less, sometimes it's a bit more. Here, it seems it's a bit less for the second environment because it's a bit more complicated. You have a lot of bands and the agents are going a bit more randomly, let's say, inside the environment. But also what we see is that if we fix a constraint of, I want at least to receive a given SNR on my communication, this constraint is already satisfied all the time. And that is what we wanted to achieve. So to give you a more, let's say, in-depth and a real case, Jaro, that is here, measured his chip. It's a chip that is a sensor interface, so it's a mixed signal circuit that has been fabricated in 65 nanometer technology. So it's basically composed of several sensors. There is light, accelerometer. Then the signal is digitized. And then compressed and stored in the memory. So basically, this is what the node will do in the end. And of course, the instinct want to schedule this with measuring what comes out of the ADC here, and let's say see how we can tune the circuit. What we can do is to select some sensors. We can select the sampling speed of the ADC. We can select the resolution of the ADC here so that we have more or less accurate signals, and then we can select several compression methods. So some of them that are of course compressing a lot the signal, some of them that are more clever but cost also more energy. And this instinct is, let's say, learned through this behavioral tree that is developed through this process. So the offline optimization phase is I want to have a behavior tree. And so how do you do that? Well, you have this evolutionary algorithm that will give you what is this behavioral tree, but of course you have millions of settings that are possible. So it will take years maybe to converge. So what we say is that we have to help a bit the algorithm. And the way that we do that is to having a pool of conditions and a pool of actions that we can select from to speed up the process. So the pool of conditions are, for example, checking which threshold we should really see in the sensors. Not all the thresholds are interesting and all these things. So we can do it beforehand. And for the action is basically selecting a subset of settings that we will choose from in the circuit. Frequency, resolution, compression settings. And this is done by, again, performing an optimization through evolutionary algorithm. So we will essentially try out multiple possibilities and build a Pareto front on what is the optimal power consumption of the circuit depending on several, let's say, distortion that you allow in the signal. So basically more accurate signals or less accurate signals, and then you pick up some points from this Pareto front and it gives you the pool. So the behavioral tree is chosen according to these pools. And once you have it, you need to implement it on chip. So the first step is to compile it. There is a custom compiler that will compile this signal into a lot of complex, let's say, coding. And then you embed this in a memory. So there is a memory in this, there's a programming SRAM in this chip. And essentially, to give you the feeling of what it does, what is encoded is, for example, I'm coming, let's say, for the first condition somewhere here. What is the threshold that I should look on which features? So features are, okay, what is the mean of the signal? What is the slope, the zero crossing? So it will tell you, look at the threshold from this, and then it will tell you what to do if the threshold is crossed or is not crossed. So, so this is, let's say, what to do next. And next, it will tell you, you should use this sensor at this speed with these settings. So basically, that's a program, and this program is running through the chip, and depending on what you experiment in the condition, you are somewhere, let's say, somewhere different around this tree. But this is really what we do and how we implement it, let's say, in terms of the circuit. So I hope it gives you some, let's say, a nice overview. And I can just give you some preliminary results. So basically, the chip has been measured for different modes. The chip can be in standby. The chip can be in a mode where you require to sample very fast, that you store less data, or for example, you store the data of one sensor, and then we see the a graph of the power breakdown. So we first have a base power, 162 nanowatts. This is what the chip consumes when it's on, basically. And then you see, for example, if you're in standby, the only thing that you do is you need to sample your sensor sometimes to see if something happens. But the rest is power gated, so the rest doesn't consume any power. So in this case, it's around, let's say, 200 nanowatts. But then you see that if you put more attention, if you have, depending on the mode that you want to be in, then you have more of the power consumption that comes, for example, from the sensing speed, that comes from taking the data in a buffer, and storing it, a lot of different things. But what you can see here is that there is a real flexibility that can be exploited by the evolutionary algorithm depending on really the case study and what we want to do. And measurements are still ongoing, so I hope you will stay tuned to see what it comes out next. So that was this presentation. I hope I showed you that we really managed to make hardware and software cooperated together to improve each other. And yeah, we have presented very promising solutions. We have a lot of ideas to improve next generation of devices. But all these ideas need to be tested at a larger scale. So of course, if you have ideas, suggestions, really open to suggestions. So thank you. Thank you for your attention.
Thank you very much, Martin. Who wants to ask the first question?
Yeah, on slide 19, you show the diagram that it looks like a marriage between a simple microcontroller and a Markov model. So with fixed programmability,
yes,
mainly using fixed states, but the transition between the states depends on the sensor. So then I get the feeling that you are kind of reinventing a wheel or so. Why don't you use, for instance, take for example the RISC-V instruction set and then add a few critical instructions that are essential for you, and then stay to a common programming model instead of inventing your own machine.
The thing is, I mean, this consumes something around 50, I don't know, 20 nanowatts. So that might answer to your question already, but so really the idea is that we want something as simple as possible. So we don't, these instructions are basically here, like you see, like there's just a few, it's basically ones and zeros that are coded, and they are coded here in this compiler. And so yes, the key is what can we do with no power, basically. So that's the minimum that we want to do, that is required. We cannot do more. It's not like a full, there's no full programmability, but that consumes 20 nanowatts. So that's also the.
Yeah, but that fixes the application space of your.
Yes.
To something that you could think of before, because you will never be able to make it more intelligent later on.
Actually, we make it more intelligent because this, like, I mean, it depends on how you define the make it more intelligent, because basically this behavioral tree can have thousands of possible outcomes. And of course, the proof of concept means that you have some defined actions, some defined conditions, and you cannot do whatever you like. But what we wanted to see is that to push it like as much as possible and say like this is really the required minimum. What can I save in terms of power? But maybe you cannot save a lot. Maybe you can save a lot more, and then gradually. What we also like to do in the future is to say now we gradually make it better. So yeah, I mean that was the general strategy.
I just mean if you have a microcontroller like thing on board, it doesn't mean that you have to use it all the time. You might need to use it when it's necessary.
But the classic processor, RISC-V processor, is a power dissipation that is like 4 orders of magnitude higher than this.
It depends on yourself how you design it.
No, because actually, so.
I mean, we don't need virtual memory. We don't need execution protection. We don't need.
No, that's true.
I think that this thing has so much, and everything that you have adds load to the clock, that adds leakage to the. We're here at the current level that is lower than the leakage of a large processor.
Yeah.
So I think for us the risk is not an option.
Yes, and then it's also, I mean, the process, I mean, the microprocessor like is in the demonstration with the bigger balls, and you can see that it's very tricky to shut it off. Or I mean, it's not like it. The orders of magnitude are maybe 2 or 3, you know, between the power that you have here and the power that you have in the microprocessor. So, yeah. But I mean, we can discuss it further. That's some topic.
Yes, please.
Martin, you showed very clearly the relation between the signal-to-noise ratio and the power that you want to send out. And of course, that's an example. That's single-dimensional.
Yeah.
Of course, you do that multi-dimensional, different parameters. Like, for instance, also you can see where it is in that complex system. So at one moment, at one position, you want to have another accuracy than later on in another position.
Mm-hmm.
On one end, you can say beforehand, I want the position dependence. That's what you put in the system, and that's how you learn it. And I want the signal-to-noise ratio dependence, etc. You can also say that these parameters also can be learned.
Yes.
How far do you go here? What do you put in? What is the information that you put in beforehand in the system, in this typical system?
So actually, what we have, I mean, potentially you can try a lot of different things. And yeah, I'm not sure that, I mean, the fact is we tried with the simple things, but there's always a trade-off between what you can gain and what you have to invest in having the circuit doing this. And the first version of the ultrasound circuit was, let's say, this simple version, so that's what we tried out. But Gonensch has now a new chip that is doing a lot more things, let's say, with this FMCW and all these things. So that's part of what we want to try. To answer your question, we didn't try more in this thing yet, but that's part of what we want to do. But definitely, I mean, it's definitely possible from the software perspective. That's for sure.
From the software, we went under to tune 23 variables over 15 objectives. 15 objectives.
Okay.
So 15 objectives and 23 variables. Okay. We tested that.
Yeah. Okay. Thanks.
Yes, please.
You just explained that this one does 20 nanowatts, which is very, very low. But you also mentioned that the basic consumption is 162.
Yes.
Where is the rest going?
So it's mostly leakage, and it's all the features that you need to have the chip on, let's say. So like clocks, for example, and maybe Aro, you can give more.
There is just the dissipation, getting the clock to the right place in the chip already consumes power. Then there is also, for example, constant feature extraction and leakage, mainly leakage. And that's the 3 main things that really constantly consume power, and that we really try to optimize. This chip is already heavily optimized to get this number as low as possible, because the lower you can get this, the more flexibility you get in your chip. But even with lots of design tricks, you still only get to 160 milliwatts for these kind of systems.
So the thing also, if I may add something, is that we are already below, let's say, state of the art in this system in terms of leakage. The problem is when you have to sample very slowly, and here leakage becomes dominant pretty fast. Even, let's say, 65 nanometer, let's say, we could say it's kind of an intermediate node. I mean, it's not, the leakage is not that high, but still it starts to be a concern. And there's been a lot of work into really saying how low we can go in terms of frequency. And this really boils down to having as less leakage as possible. But yeah, at a certain point, you're just constrained by the technology.
You had a follow-up question.
Yeah. So the 162, I'm now wondering, is that the power consumed from the battery, or is there a battery converter in between?
No, this is the power measured, like that's the circuit only. There's no battery. Yeah.
If the leakage is the dominant power consumption, would it be attractive to use an older CMOS node with less leakage but higher dynamic power consumption?
Yes, I totally agree.
I don't.
No, I mean, I think it's a problem of like, also we have the IP, so this is like a mixed signal chip, so we had two chips together. So of course there are concerns about technology, but Yaro disagrees with that, so let's
So you want
hear
to
him.
take this outside? Or?
Basically, there is also a constant power dissipation because of a fast clock. So this chip, to drive back the leakage, we power gate, so we first gather lots of samples, and then in a burst, we calculate everything through, we send it to the memory, and so on. This burst clock needs to be faster. This burst clock also is consuming active power. This, and even if you clock it, it still is going to a few blocks where it's constantly loading up and down capacity, and this capacity is node dependent. If you go to an older technology, this capacity becomes bigger, and then the leakage power indeed goes down, but this constant active power is probably going up. And I think 65 nanometers is a quite good trade-off there. But it depends on the sampling frequency. If, for example, you only are interested in accelerometer, which is around 100 Hertz sampling frequency, then you can indeed go to older nodes. If you are interested in sound, which might go up to 100 kilohertz, then it might even be interesting to go to even newer technologies. So it's really a trade-off there on the sampling speed.
What supply voltage do you use? Because if you have lower
this is one of the shortcomings because of time issues. I have one chip that runs at 0.73 volt. I actually tried to aim for 0.6 volt. This is completely possible if you have the right models of your standard cells.
Yeah, I know.
We did not have enough time to get the right standard cells, and this is why the chip is only perfectly stable at 1 volt, and if you go down too low, it becomes unstable, even though in theory it's perfectly possible, there's no issue with that.
Okay, thank you.
Further questions? If not, then let's thank Marcel once more. And then we'll continue with the presentation by Peter Halpe, who is going to explain to us what happens once you decide to do something. How will you decide? Thank you.
Sorry.
I think for people remotely, it's nice to have this consistency between the two sounds.
All right, I hope it's working, so welcome. I give a talk about the miniaturization of the circuits, the transducers, the devices within this project. And I think the earlier speakers have already explained why this is important for us. Before I start, I should also mention that even though I give the presentation, the work what I present is actually done by several persons, Gonench, Haoming, Martin, and Sina, together with the supervisors, but I'm here to present a brief overview showing some technical details, some examples of what has been done. So what is already clear to you, I think, is we're going to work about sensor swarms, and in order to collect information, there are kind of a few essential things. First of all, we want to add sensors. I'm not so artistic, so they just look like this. We want those sensors to be versatile, because we don't know exactly beforehand what we want to sense, and we want them to be power efficient. The second thing is that we don't have single sensors, but we like to work with swarms, and that's only useful if you let them do something together. And that means that we foresee that they should have some form of communication to really work as a network, and also to be able to do ranging distance measurements between the devices, so afterwards we can kind of reconstruct the orientation or the location of this network or even the environment. So that's why I'm going to talk a bit about sensor interfaces as well as ultrasound transducers and circuits that we use for communication and localization. So starting with the sensor interfaces, versatility. In what sense? A few things. The first one is we have seen that maybe for different applications we want to use different type of sensors. And we don't like that every time we have a new experiment we have a new type of sensor like temperature or pressure. We don't want to develop a new ASIC again and again and again. So ideally we try to make one ASIC which can work for many different type of sensor elements. And as you might know, some sensors they produce an electrical parameter in a resistive domain or capacitive form. So you want at least an ASIC which can deal with resistive and capacitive sensors. The second problem is that if you look to available sensor elements, so here is a plot of different capacitive accelerometers and pressure sensors, you'll see they have a lot of variation in terms of the capacitor value that they have and the range that they occupy. For example, these two designs, they have maybe a similar value, but the range of this one is much bigger than this one. Or these sensors, they actually have a much higher nominal value. So again, here you'd like to have a single interface that can optimize the range it can cover, dependent on what you actually connect to your interface. Besides that, after you have chosen your device, you may still want to adapt things like the measurement rate or the precision with which you measure. And this was shown by the previous presentations because maybe in different zones, you have different requirements of the data that you want to collect. So we want to be able to change all those things, and of course we want to remain efficient, that if we reduce the performance requirements, we also want to save power. Otherwise, there's little point in making it adaptive. So first, knowing this background, the question is kind of what kind of topology, what kind of circuit type are we going to use that is versatile? And the first discussion here is about circuits that are either biased with a static power consumption or with a dynamic operation. So if you look at that, if you have a kind of an analog circuit which has a constant biasing, it means that the power consumption does not change dependent of the operating frequency at which you use the circuit. On the other hand, dynamic circuits, which are, for example, very typical like digital circuits or like switch capacitor circuits. In that case, for dynamic power consumption, you'll see that the power scales proportional to the actual frequency at which that circuit operates. That's one important difference. Now, if you normalize the power to the frequency, then you can calculate the amount of energy a certain operation takes. If you do that for these two cases, you see that for dynamic operation, the energy per sample that you sense, for example, is constant regardless of the frequency of operation. But for the static design, you actually see it improves with high frequency. Or maybe I should say, it actually degrades if you go to low frequency. In fact, for the static design, you see that it's only reaching the optimal energy consumption if you use it up to the maximum speed that it can work at. Below that is suboptimal. And that's an important difference once we try to improve efficiency with versatile settings. Because if you think about the operation frequency, you can use this in two ways. If you change the frequency of operation, you can change the rate at which you do measurements on your sensor, so the sample rate. But secondly, you can also use a high operating frequency to use something which is called oversampling. You measure the same thing several times and you average it to get a more accurate or more precise result. So enhance the resolution. If you combine that, you can actually express the actual operation frequency as the multiplication of the rate with which you want to sample, multiplied with the extra factor that you need in oversampling to improve the resolution. Now you can make a plot over here where we see, let's say, the performance chart in terms of the sampling rate, how often do we want to sample our sensor, versus the oversampling rate, how accurate do we want to make the sensor interface. And the red line here is a line which connects the points where OSR times F sample is constant, so that has a constant operating frequency. So for the static bias design, we know that that design will only be optimal in terms of efficiency if you use one of those points of this line. However, if you design an interface which is dynamic power consumption, it can remain optimal in terms of efficiency for any setting up to this line. So this gives you much more versatility in the settings where you can maintain the energy efficiency. So this is, in this explanation here, giving the motivation why we want to make sensor interfaces which have a dynamic power consumption, because it allows us to inherently save power as a function of the resolution or speed requirements that we have. So the next step is that we're going to look to a few basic sensor interfaces And we're going to see how we can change those from a static to a dynamic bias design to enable this versatility. So over here I'm showing you one simple example here. This is a resistive bridge. Normally you connect it to a supply or a reference voltage. You have a reference resistor and a resistor RS, which is your sensing resistor. The output voltage that comes out of this bridge network is a function of the sensing resistor, and in that way you can measure things like temperature or stress if you have a sensor device which is dependent on the temperature or the stress. The problem with this one is that you see it has a static power consumption because of always current flowing in this bridge. To make it dynamic, what we simply do is we remove the fixed supply, but we add clock signals to the top and the bottom. If you put the clocks both to a low level, the device is turned off and not consuming power. And only if you have a clock pulse on one of the two sides, there is a voltage across the bridge, there will be power consumption, and you do get an output signal. So the clocks can both enable and disable the circuit. But secondly, there's another opportunity now, because we can turn the supply around. We can actually have both, let's say, a positive supply or an inverted supply applied to the bridge. And this has advantages, as you'll see later in the presentation. So how do we now make our sensor interface? You can say this resistive bridge is able to measure a parameter that we want to sense and translate it to a voltage. Now we need to digitize this voltage to be able to connect it to the digital processing unit. So this is done with an analog to digital converter. Here modeled in a simple way, just as a sampling device and a capacitor, which is kind of a typical model of an ADC. Now what we're going to do is as follows, because we want to use this in a dynamic way. We first switch on by means of the clocks this bridge. Then the voltage at the output of the bridge is going to charge the capacitors in the ADC. And as long as these capacitors are charged, I keep the bridge on. But at the moment that I reach my steady state level, the capacitors are charged. Then I can completely disable the bridge to save power. And then I can do the conversion of the signal that I sampled in the ADC. The nice thing is that your bridge is not always on. It's only on for a short time, dependent on the RC product in this network. And because of that, the energy that you take now is actually not anymore determined by the resistor value, but it's actually determined by the value of the capacitors that you need to drive, the parasitics as well as the capacitance of the ADC. And that's interesting because normally you expect that larger resistors, less current, lower power. But that's not true here, because larger resistors, even though it gives less current, it means you need to be on for a longer time. And it means in the end the power does not anymore depend on the resistor value. So that's why now we can do the opposite. We can make the resistor small in value. And by that you save chip area. And you in fact also reduce the parasitics, which is actually going to save you power in the end. So it's opposite to what you traditionally would do. Now one more thing, because you know the energy depends on the capacitance. So one question is still, how small can you make the capacitance of the ADC? So for that reason there's a tension in the ADC trying to minimize the capacitance, and we do that by a custom design of the capacitors inside the DA converter. I'm not showing you all the details. This capacitance is less than 0.3 picofarad, which is a very small number. And because of that, you're able to save power in terms of driving this ADC. It's also an asynchronous ADC, which means in terms of clocking, you just need a single clock edge to activate the entire ADC, rather than having to provide multiple clock edges, which would also complicate the system. So how does it operate in practice? Here in the timing diagram, first we turn on the bridge for a certain time, enough to charge the capacitors in the ADC. When this is done, the bridge is turned off, and we perform the digitization to obtain a digital code representing whatever we want to measure. By then, we are in fact ready. We do have an output code. We have our measurement. But now, optionally, you could do a second measurement. And in the second measurement, we do the same thing, except that we switch on the bridge the other way around. And that means that your circuits are kind of inverted, and the output value that you get is also an inverted value. Except that certain problems like offset or 1/f noise, they are not inverted. And that means that by combining these two outputs, you can get more precision in your conversion, because you cancel offset, 1/f noise, and a few distortion problems in the converter. And in that way, you spend 2 measurement cycles now, cost you more time and energy, but you get higher accuracy and resolution. Now, if you have time, I'm going to skip this slide over here. I would like to show you a few results. So in this case, we have an interface which is a resistive sensor bridge together with the ADC. And in this case, the resistive bridge is actually completely on the chip, where the sensing resistor is actually a temperature-dependent resistor. And in that way, the whole interface becomes a temperature sensor. To show you the difference between using large and small resistor values, there are actually 2 resistive bridges here, one with small resistors and one with large resistors. In practice, they can do the same thing, but you will see that the large one is going to consume more power because it has more parasitics. So a few measurement results. Here you see the output code, the digital code, is a function of temperature for the 2 bridges. You see they have similar behavior. There's a difference in offset, but it can be just to mismatch. If you look to the power consumption, you see a few things here. You see power versus speed. You see indeed that the power scales proportional to your speed over quite a large range, down to a level where you hit the leakage number, which is very small in this case. The second thing you see is that the large bridge with the large resistors, shown in blue, it consumes much more than a small bridge because it has more parasitics. And also because of the large resistor, the RC constant is higher, the circuit is slower. And that means that the maximum speed at which it works is also lower compared to the small bridge. So the advice is clear, go for the small bridge. Well, here's something about oversampling. So you see that the more you oversample, the better, the finer the resolution of the interface becomes. With single-sided, at some point you're limited by 1/f noise, which is a correlated noise source, and then oversampling doesn't really help anymore to improve resolution. But with double-sided measurement, you see if you subtract the 2, you go down further because you can compensate 1/f noise problems. Same thing for accuracy. You can measure just a single sample, or you can combine 2 samples and subtract them. And what you see is also the accuracy is improved because certain nonlinearities are also compensated by combining the 2 measurements. So I will not really go into detail there. Just as a benchmark, over here you see existing temperature sensors in terms of how much energy do they consume for a conversion versus the resolution that they get, the precision in Celsius and degrees of the interface. Now the point at which we focus is for our kind of application is clearly where the energy consumption should be very low. At the same time, for resolution, we're relatively relaxed. We're not aiming to measure the temperature with a precision of, let's say, 10 microkelvin or something. For our application, we think about something like 1 degree or 0.1 degree of resolution. So this is indeed the area that we reach in the end in terms of the resolution. And you see that we do this with a very low energy consumption. You also see that most of the other works are single points because they are really optimized for 1 point. But we cover a bunch of points because we can change the speed as well as the resolution in this design. Now this was a lot about resistive sensor interfaces, but not everything is a resistive interface. For example, pressure sensors, accelerometers or other devices, they may be capacitive type of sensors. So in a similar way as you make a resistive bridge, you can actually also make a capacitive bridge and connect it to the ADC. So I'm not going so much into details, but here we have a capacitive bridge which you can interface to capacitive sensors, and then we read it out by the ADC. Because everything is dynamic, you can quickly operate in the individual parts. It's easy to connect multiple type of interfaces and multiplex this all into the same ADC. So as one example, I want to show you the system that actually was demonstrated by Jaro, where 3 different interfaces are connected to the same ADC. And over here you see a measurement example of that single chip, multiplexing 3 different types of sensors simultaneously. So we have on one hand the temperature sensor that I show. Second, we have a capacitive accelerometer, which is connected to our interface. And third is a pH sensor, which is essentially also a resistive device. We sense these at a relatively low speed because we think maybe as an example here, 1 sample per second for temperature, for example, is good. The others are a bit faster. We measure over time and we compare what we measure against a commercial reference in blue for the different types. So what you see is that our device can follow the trend of the commercial device in the same way. At the same time, of course, we have very low power consumption, so you see our result is more noisy. Our results in red, they have a bit more noise around the measurement as compared to the blue ones. However, we managed to do all these measurements simultaneously with a power consumption of only 1.4 nanowatts, which is really very low. The commercial devices, they are indeed more precise and more accurate, but they will consume in the micro or milliwatt range. So this is a very big step. All right, so far about sensor interfaces. I also want to quickly say something about the ultrasound components. So on one hand, used for communication. On the other hand, used to measure the time between sending waves to measure the distance between modes. So we have done developments on two aspects. On one side, to develop ultrasound transducer components, and on the other hand, the electronics, the transmit and receive electronics, to connect this to the electronics. So for transducers, I want to give you a few examples. The first one here was the first development, is called a resonating shell. So in this case, we have two discs which are made with piezoelectric material. And on the outside, you have a shell from ceramic material, if I'm correct. What happens in this case is if you activate piezo discs, the entire shell will actually resonate as a result of that. And because of that, you have a relatively omnidirectional transmission, which is nice if you don't know the location or the orientation of the sensor modes. It is relatively small, but it also has a few disadvantages, and it's relatively difficult to manufacture, to integrate with an ASIC. And also, if you look to the size, actually, the remaining size inside is also relatively small. So we did experiments with this one. Here you see a few examples in measurements. You see the resonance frequency as well as harmonics. And over here you see that it's a relatively omnidirectional pattern that this device transmits. Based on these results, it was decided to move forward with another technology based on MEMS devices. So on a MEMS technology platform, you can make very small structures. By adding piezoelectric material, you can also make transducers here. So in this case, the scale is much smaller. So like a single transducer is like this, about 0.4 millimeter in diameter. Usually you combine these in an array to make a bigger device, which is then, as a whole, your transducer. So in this case, you can change the size of the transducers if you want to change the resonance frequency. But because you have an array, you could actually also do more advanced techniques like beamforming if you would like to do so. For single PMAT devices, there's some limitation, and that is if you want to go to lower frequencies, which is helpful if you want to go to larger distances. The problem is you need to make those PMATs bigger and bigger, and then at some point, especially for those large devices, you will notice that even though you apply an electrical signal, most of it is not transferred in acoustic energy, but it just stays electrical. So you don't get a nice wave. So to solve that, there's some innovation in how to implement these designs. So over here you see a PMOT array, but then by construction, this is embedded into a box. And when you expose it to water, first the piezo elements are activated, but as a result of the vibration of these elements, actually the entire silicon piece over here is going to vibrate as a result of that. And because that one is much bigger, you get a higher transfer to acoustic energy. Also, because it's a bigger device, it also enables you to resonate at a lower frequency as compared to the individual elements would otherwise do. So in this way, the resonance goes down, which is helpful to increase the distance. But at the same time, because you started with small PMATs, you still have a lower parasitic, which helps you to save power in driving this. In the end, improving the efficiency. So over here are a few pictures of how this is assembled. You see the array of transducers. And then with epoxy, it's fixed to the board. And on the back side, you have a cap to shield it from the water. A few measurements are shown here with different voltages and different distances. And the message is in the end that with a 1 volt driving signal, we can reach up to 50 centimeters with still a pretty nice signal swing. So in theory, this kind of, in practice, this actually demonstrates that you're able to cover distances in the order of a meter with relatively small voltages and relatively small devices. Finally, something about the ultrasound electronics. So you need something to drive a transducer, and you need something to recover the signal from the receiving transducer and get a proper electrical signal. Now what you see, we have developed different generations. I'm not showing you all of them because not everything is ready yet. Some are still ongoing in terms of experiments. But what I see is in the development of these blocks is there's quite some similarities to low power RF or wake-up radios, for example. We have seen things like envelope detectors coming up here as well, and also in terms of the driving. To show you two examples, over here is a transmitter. It's very simple in the end. You could kind of model the ultrasound transducer as a capacitor that you need to drive. The only problem is that usually it uses a voltage which is a bit higher than you can use with standard CMOS supply voltages. So we have here a level shifter to boost the voltage to a higher level, up to 3.3 volt, and then large inverters to drive the capacitance of the transducer. Essentially, the power that you need to transmit is then given by this equation. It depends on the speed, the capacitance, and the driving voltage. Now this formula is kind of inherent, but you can still improve that, for example, using a multi-level transmitter. In that way, you can actually improve the efficiency of this system by tens of % and save power. And it's quite important because the capacitance of the transducer is not a small value. So in a newer design, there's actually an on-chip DC-DC converter to make multiple voltages, which is then used by the transmitter to charge the capacitors in steps, which is more efficient than charging it at once. If you look to the receiver, I would like to show you the LNA, the very first block in the receiver, where the efficiency is most important because there you deal with small signals. So also here you see techniques which are familiar for RF or for analog design, but are still new for ultrasound receivers. So in this case, the input stage, the LNA, is an inverter-based design. That's a known technique which kind of improves your efficiency by a factor of 2 because you reuse the supply current for true transistors. The transducer is AC coupled into this LNA, while the DC bias is provided by the resistors. The ADC that you see here is exactly the same one as I show you in the sensor interface. And because it's versatile, it is used there at 1 sample per second, but here is used at tens or hundreds of kilosamples per second or more. In terms of measurements, I think Gonish has already given you a nice demonstration for localization. We've also done communication experiments. So this is actually still not public, it's soon to be published. But I just want to give you a few numbers just to show you where we are. So you see for communication, distances of several meters, data rates in the order of a kilobit per second, and the energy that is used is in the order of tens of nanojoules per bit. And it means that the total power consumption when everything is active, you're talking about tens of microwatts for the transmitter and a few microwatts, if I'm correct, for the receiver. Of course, dependent on the activation of the system. So very briefly, a few conclusions. I tried to show you a few examples of what we have been doing. I hope you're convinced that we managed both to save a lot of power, but also to make very small and compact designs. So these are really critical steps to enable the future miniaturization. I show you a few techniques which are able to reach this. And I think I would like to finish with a few references in case you want to know more. And of course, to acknowledge the EU, Murata for sensor devices, and thank you for your attention.
Thanks a lot, Peter. Who wants to ask questions? Any questions? Yes, please.
So the last sensor you talked about is, what was it, ultrasound? That's a mechanical device, in fact, isn't it?
Yes.
Do we make use of the national resonance of such a device? Or?
Maybe Sina, you can comment on that? Yeah. So the question is, do you use a natural resonance of the device here? You have to, huh? Yeah, it's a bit what you see here. So if a transducer is designed, it has resonance modes, and the transmit electronics would need to generate a waveform at this frequency to get the system working.
Is that an intelligent loop that let's say,
no.
To the resonance frequency?
No, so at the moment what we do is we characterize the transducers, or if we use commercial ones, we also characterize them to understand where is the resonance. And then let's say the waveform which goes to the transmitter is programmed at that frequency. Yeah. Yeah, but I could imagine indeed you could do something more intelligent indeed. Yeah, true.
Further questions? Yes, please.
I noticed in the receiver on the something I've heard before, but there you have basically invert phase amplifier, but it's an open loop amplifier. So that of course makes it very simple and gives you maximum gain, but what does that mean for linearity and things like this?
Yeah, I haven't shown.
Does it matter in this setting?
Yeah, there are two things. I haven't shown you exactly the entire circuit, but I believe it's correct that it's open loop. Is it, Konenj? Yeah, exactly. And I assume the open loop gain is not extremely high. Yeah. Do you know roughly the number? 32 dB. Okay. So that means it's manageable in terms of not saturating. But there's another loop which sets the bias point correct.
Further questions? If not, sorry.
Yeah.
What's limiting the sensitivity of the ultrasound receiver? Is that the LNA or in the transducer environment?
Yeah, it's a good one indeed. So it could indeed be the environment or the transducer, or if I could imagine if you have a certain pipe and there's disturbance, that's kind of a background noise, which also will kill your sensitivity, so to speak. Yeah. But it's really environment dependent.
Because if you have a complete RF receiver, then you would have more gain stages and to get more sensitivity. So could you improve there by adding a little bit more power consumption?
Could be, but Konenj, do you think that would be useful, or are we limited by the environment more?
You think in this environment we also control the unit distance and the transmitting power we apply. In this case, it is the sensitivity is more or less known for a given distance and environment.
Yeah.
But if we didn't know that, indeed, there is a risk that the chain is saturated. It's true.
Maybe also here this example of the transducer measurement. Here you also see, there's an example, depends really on your transducer, of course. In this case, you get a signal like a millivolt. And that is small, but it's not as small as you do get with RF.
This is generally optimization of either optimizing sensitivity, so you can increase power distance, or you can reduce your transmitting power so that you know the receiving power will be less than the
because the transmit power is a lot higher than the receiving power, so having a little bit more receive power and then less transmit power would probably have total lower power consumption.
Yes, it's true.
Yeah. But then indeed you still depend on the environment. If that's super noisy, it's not going to be helping too much.
And it depends on the amount of time that the receiver is on and the transmitter is on.
Depends on the cycle.
Yeah, true.
In this example, this quantum is on. To be fair, reality to this cycle.
How do you coordinate that the duty cycling works okay, or is that not really worked out yet?
In this case, that's not worked out, but it's in the end something that should also be done by the instincts to decide whether or not to communicate and how often to do localization measurements, for example. Indeed, if you keep on doing this continuously, it costs a lot of energy. If you're going to do this once in a while and you multiply it with the duty cycling factor, it's going to be very low. But that's indeed exactly the thing. Huh? What I describe here are the circuits, and the idea is that they cover a range of settings. We provide the knobs, and then later the instincts decide what to do with the knobs.
Are there any urgent final questions for Peter in view of the time? If not, then let's thank Peter once more. I do realize that we took a little bit more time for the demo than we should have. My apologies for that. So we're running a little bit behind schedule, but we're also close to the end. So the last presentation today is by Heinrich Wörtje, and it's a shorter presentation where he is going in a short time explain everything about future industrial applications of this technology.
Dit is een Apple, dit is nog goed. So, take that one, right?
Ja, andersom. Ja, dat is beter.
That's better, right?
Ja. En dit is voor remote.
No, that is not working this now. Forget. Just keep it.
It is working actually.
I stay here though. Okay, given the fact that we have been talking about so much instinct, so my instinct tells me that it will be shorter than 15 minutes, so I will try to make it in 10 minutes, right? So the interesting point is that just before leaving you to the drinks and to the discussions, I think this is now the point really to try to make a link between a lookout, what really this kind of beautiful technology, but also the concepts could actually mean in a wider context. And when I was asked preparing this presentation, I must say at the moment I'm also involved in the north of this country in setting up a digital innovation hub, so digitization and Industry 4.0 is at the moment in my mind. So I was really digging a little bit in literature and also in the activities, and I was wondering what actually in this very, very important topic these developments might mean, and I think that naturally would be an interesting discussion. And first of all, let me set the stage. Most probably all of you have seen that, so this is a commonplace. This is most probably very common to you, but just that we have all the same baseline, let me remind you what actually Industry 4.0, the revolution we are presently inside, actually means. Many people make the mistake that they claim that Industry 4.0 is something like computers and robots are coming into our production lines. But this is not the case. This is beyond. This already happened. What at the moment is happening is a tremendous new step in digitization. Digitization is the driving force between and after Industry 4.0. And what does that actually mean? Just the last gimmick and then we really get serious. What it means in that simple representation, so you have a physical factory, and this physical factory, basically all components, all devices, all incoming streams, all products, and I will come back to the products in a minute, will be equipped with sensors which are basically providing the information that you can provide, all this information, the performance of machines, the aging of machines, the status of the products you're producing to a cyber environment where in, let's say, this cyber environment, inside the computer, every processes, the optimization, the improvements of your product is shifted into the cyber world and there it is taking place. This is Industry 4.0. But this, I think most probably you have seen before, but Industry 4.0 comes with much, much more feasibilities. And in the north, for example, we are collaborating with a company most probably also known here. I've heard already heard this name, so Philips. And because a lot of male are sitting here, but also female most probably know this device, a shaver. In the past, the shaver was like that. You went into the shop and you were buying a shaver and then you were using the shaver. But this is not what Philips wants you to do in the future. What Philips wants you to do in the future is this. So your shaver is equipped with enormous amounts of sensors and measuring everything. For example, the way how you shave, the efficiency how you shave, how the shaving is changing in the morning, in the evening, with aging, the shaving between people coming from China, the shaving between people coming from Europe, and so on. And all of this information is fed back again in the cyber physical world. And in this cyber world, Philips will be capable, for example, of training you to really optimizing your shaving. But also, for example, detecting that something is going wrong with your skin and maybe you're developing a disease and whatsoever. So basically your shaver will become your personal shaver only. It's your product. And it's not a product you just buy. No, it's interactively changed and changing and training you. This is basically what is the vision behind that. Now, this is actually a very interesting concept, and indeed it is really worked on. And for example, the sensors going to the head of the shaver, that's one of the developments we are involved in. But if you're feeling what that means is, Cisco, for example, is estimating that in the year 2030, with all these devices equipped with sensors in the industries, but also at home, we will cross the line of 100 billion sensors delivering data into the Internet of Things. 100 billion sensors. This is an amount of data which is just unbelievable. And this is the context I think we are looking into. And this will also be on the level of energy consumption will become very, very significant. At the moment, just to give you an idea, in the United States, alone the storage of data is on the level of 10% of the total energy consumption of this country. This gives you a feeling. So this is getting significant and not just simply something you can ignore. And there I think Phoenix comes into game in a very interesting way, and this is what I would like to show you in the next 5 minutes. Because I was actually looking into the concepts people have developing this model of the cyberspace. How do they actually think that? You know, I'm not coming from this world, so I was really going into literature. And I found one interesting concept, and this is shown here. This is called the 5C concept. And what you see here is that actually there are 5 levels. And the lowest level, going from the lower level to the next higher level, is always producing data for the next higher level. And this is, at the end of the day, top off, there's the human and looking at all this beautiful world. In the lowest level, level number 5, we have the sensor, we have the sensor networks, we have the communication, we have the functionality. Then we have the conversion, the data analysis, that's the level number 4. Then we have the cyber level where actually the model is formed, which is used then for all the further steps. And then we have the high level 2 and 1. So this is, let's say, the concept, for example, people are working with, and what I like is the 5-level architecture specifically focuses on how to enable physical machines to utilize data and information coming from level number 5 and 4 to create knowledge and wisdom then in the higher levels. And this is taken from a PhD thesis, which will come back in a minute. And the enabling technologies you see here, so we are talking about sensing, communication, computing, cognition, autonomous control. This is basically all the technology you have to develop to get these things going. But now make that concrete. What does that mean? I'm coming back to the example of Kai. So what we had here, I will not, just to remind you, we had this sensor in this bubble chamber. These were the parameters we were measuring. And what we are interested in, at the end of the day, the important information request is the bubble flow and the bubble distribution, that we can put that into our model, the cyber physical world, the cyber physical model of that device, so that we can optimize it. This is, in the language of Industry 4.0, what we would like to do at the end of the day. Now what we have seen is basically threefold. First, we had this high-speed camera on top. We had sensor data we could use for the calibration, actually the ground truths. So we had some ideas what the bubbles are, what the flows are. This was measured independent from the actual sensor we are interested in. And then the lower parts are the output from our sensors, and there already it starts. For example, alone the signal we got was very complex. And the first thing what we had to develop was an educated guess. What is actually the model? What is the information in the signal? We made a choice. And indeed we see 3 sections. We see the red one, the green one, and the yellow one. Most probably, and this is what Kai was also showing, the red one, we have the amplitude, which is obviously the sensitive part that was used by the student. Then we get oscillation, which might be interesting or not, and then because it was hanging on a thread, I think the yellow one is the reflection and the ball is coming down. And then using, for example, now the amplitude from the red part, we had, for example, some ways we could look at the rotation, we could look at the acceleration, we got some calculations, so we have seen the sensor is sensitive. This is the status what we have at the moment, and I would call that generation 0 in the language what was also used today. But now how do we get further in this process of actually forming a reliable cyber physical system? How do we do that? And that means we are coming up with a lot of question marks. Because at the end of the day, and this was also discussed today, who tells us that the sensor we are using and the parameters we are sensing are the good ones, the sensitive ones? Who tells us that the model what we have from our signal is the correct one? And at the end of the day, who tells us that also the parameters we are measuring again are in the correct way and are the sensitive parameters we actually should measure? At the end of the day, how do we get from the status what we have at the moment to the model required, reliable, so that we can actually handle this device, this big device, in a reliable way, in the cyber physical way? That's the big question. At the end of the day, we have to answer that question, right? This is what we have to do. And what it means is now making a mapping, going back to the cyber physical world. It means that actually the Phoenix project is mapping to the concept of the cyber physical way in that way. The lower 2 levels, so let's say the sensor data, the measuring, the data analysis, and then the shaping of the model, this is actually where Phoenix in the developments what are done within the project, the co-evolutionary cycle and the reincarnation cycle is actually acting on that problem. This is one way how you actually could produce your model require to have a reliable cyber-physical system, even if you have not generic information, even if you have not, let's say, the fundamental physical understanding what's going on there. And I'm rather sure that there will be no PhD thesis. Somebody will investigate how a ball, for example, is oscillating in a liquid. This will not happen. But with Phoenix, we are developing the tools that, based on the sensor data we have and with the mechanisms we have of this reincarnation of the hardware on one side, and on the other side of the evolution of the models, we have the co-evolutionary concepts that we have in a systematic way. We can come from these measurements with a lot of question marks. We actually can come to the development of reliable models, helping us to shape the cyber-physical world of all these devices. And there are many, many problems like that. This is, for example, the aging measurements of machines, which is strongly depending on the way how these machines have been used in the past. You start at measuring, let's say, after 5 years of operation. For example, I'm rather sure that any tank has its own specific features which slightly will change the model you need for controlling that. For that, you need a mechanism, and I think Phoenix might provide a very interesting base to solve these problems, to come to reliable cyber-physical realizations of the models. And also, Phoenix, on the higher levels, Phoenix is active. I think the human interface, the way how, for example, knowledge is elicited and then coupled back to the lower levels, also that is something which is absolutely inside the Phoenix framework and is developed. And also that is extremely interesting in this context of developing these reliable cyber-physical models. And what really then hit me, that I'm saying something, the interesting thing is that in the community, I was really amazed, they actually have the same idea. There is research ongoing, there is, in the PhD I'm quoting here, you can see there is the idea that they actually would like to come to a way of the so-called self-evolutionary cyber-physical systems. They have recognized the problem. The problem of what we have is not our problem alone, it's a global problem. And there is indeed an ansatz, and which is described by a PhD coming from Lisbon, saying realization of cyber-physical systems that are not only capable to coexist in ever-changing environmental conditions, but also have characteristics for self-adaptation, self-configuration, and eventually self-evolutionary. These are the features he requires to solve these problems. And this, I think, is exactly what we discussed in the afternoon. Not perfectly matching, I'm not saying that, but the ideas are very similar, and the technology base, which is here, can be extremely, extremely interesting in that context. Therefore, my conclusions, and I think I kept my 10 minutes, very good. I think with that, and this is just 1 week of research, I really took some time, but this is just the beginning, I would claim potential application in the field of Industry 4.0 are spanning from straightforward, this is, for example, what we should do as a next step. It's rather clear what we have to do, and this is on the way to our cyber-physical system. But you can also make it very speculative, what that could mean if you really spread it and connect it to the ideas living in this community, and how far you can go and how far you can translate the Phoenix concepts, let's say, of really generating, for example, think on this Philips concept, how far you can go there. Therefore, I think the sky is the limit, I think, but it's very, very interesting. And what is absolutely clear is that would help Phoenix and the technology we have been developing to really high relevant applications. It would be a very interesting field to check what kind of applications could be really pushed forward to applications of Phoenix technology. And at the end, I would like to conclude the interesting thing, and that was really for me very, very surprising, the cyber-physical system community develops basically a coherent approach. When you're reading the publications and, for example, the thesis, and you close your eyes, you would claim it's Phoenix publication. It's really amazing. The same nomenclature, the same ideas. It's very similar in thinking what we are doing, just coming from the top approach. Thank you for your patience.
Thank you very much, Heinrich. Who has questions for Heinrich? I think people are slowly thinking about drinks. Maybe we can, oh sorry, Arthur.
Just remark, you can even bring this to the IC field. Even if you look to the evolutions in the IC field, in IC design field, you see the same evolutions. So we have to combine all those.
Yep. And that we have to initiate the discussion, I think, because people have to be aware from that community and other communities what is really available. That could be very, very interesting.
Okay. Further questions? If not, then I would like to thank Heinrich once more. Yes. Otherwise we have trouble. And then, ladies and gentlemen, we are coming towards the end of this afternoon. There's one thing I really would like to do. As you know, I've explained at the beginning that the presentations were done by senior researchers for practical reasons. But the real work was done by PhD students and other students of the various organizations. What I would like to do is to put them in the spotlight at this moment, because we even have a real spotlight here. So I would like to invite all students that have worked on Phoenix to come up here. And if you're doubting whether you're in that category, there's a very simple rule of thumb. If you did real work, then you should be here. Please. Elena, I suspect you also did some real work. Dirk-Jan? Well, if you use the rule of thumb, then yeah, you worked as hard as a student. So, so ladies and gentlemen, can I have a round of applause? And that concludes this workshop. Thank you very much for your attention. I really appreciate you all coming here. And also thank you very much to the people that are watching this through YouTube. Thank you very much. We will conclude the transmission now. And for the people that are physically here, we will have some drinks. For the people at YouTube, you will have to make some arrangements yourself. Thanks.
Thanks.